Then you're going to hear mostly from Martin and Mike. Martin is in, he'll introduce himself, but he is in tech support and special quoting. Some of you have probably dealt with him. And then Mike is in engineering. So they'll be doing most of the presentations. And then we will do some demos in the lab with Gary. Our first demo is in the afternoon. But what we'll start with is my intro. Then Martin will do a section, and then we'll do a plant tour. So for all the plant tours, for the plant tour and all the demos in the lab, you'll have headsets right at your desk. It's a big group, so we're not screaming. And then we have safety glasses in the back for those, okay? So when we do those, make sure you grab that. And then we'll have a break. This agenda, the times are loose, like I said. Depends on how many questions we have. We'll do another section from Mike, and then we'll have lunch, and then a couple other sections, and then a demo. And then we'll go back to the hotel before dinner, and then go to dinner, and then start all over tomorrow, right? Okay. Any questions for me so far? Like I said, if you want to grab some coffee, go ahead. You can do that now while I'm talking. It doesn't matter. Something to drink back there. Okay. Just a little intro to LMT Onsrud. You'll see in here. This is kind of our motto. This is how we think and act for your success. We believe we're the best in class, based on a joint development between our manufacturing strategies and our tool solutions. So our actual design of the tool to match the machining strategy. What are you routing? What are you milling? Etc. How big are your parts? What are you trying to accomplish? We are also, performance. We want to reduce. What we want to do is we want to reduce our customers, right? Your customers are our customers, the end users. Reduce their production time, right? Make them profitable, right? How do we improve their processes using our tools to make them profitable, right? And we're continuing development. We have a new product development process that I run here, and we're always developing new tools. We're always testing new things in our lab. Okay, when you go to the lab, we don't make anything there. It's all for testing. Whether we're testing carbide grades, or we're testing coatings, or we're testing geometries, etc. We're always testing for new things. We're always trying to continuously develop. And customer service, we got John back here. He's one of our customer service people. So we try to be as fast and as we can and as flexible as we can in our responses to get you guys timely answers to things. Okay. As you see John here, and you see some other guys from LMT. So we put all of our new employees through this seminar too. So we have 3 guys in the field that are here that haven't been to one yet, and John's been with us less than a year. So we don't expect them to go out in the shop, go out to the customers and sell like John in inside sales, but it's very good for him to know a little bit more about everything when he's talking to people, right, on the phone. And then we'll have Brandon. He'll be here later. He's from engineering. How are we organized? So you hear LMT tools, you hear LMT Onsrud. How does that all work together, right? So we are part of a big group called the LMT Group, based in Germany, and they have two companies in the LMT Group. It's Spindle Compacting, which is totally different. So they make tablet machines, manufacturing machines for pharmaceuticals. Okay, totally different company. And then we are part of the LMT Tools Group, where we develop, manufacture, and sell high-class precision tools. How does that all fit? Tools, okay? So we sell 3 brands here in the United States. Okay, Tools is not a brand; it's a company. Okay, it is the company, and the brands are LMT Fede, which are injectable tooling, thread rolling, etc., like that. LMT Keeneger, more advanced tooling for the automotive industries, finishing tools for mold and die. And what we're talking about here today and tomorrow is the LMT Onsrud brand. So we're making mostly solid carbide round tools for woods, plastics, composites. We're making end mills for titanium, aluminums, things like that. We are focusing on woods, plastics, and aluminum sheet in this seminar. Okay? So that's kind of how it all fits. So all of our sales out of this office, we sell all three of these brands. Okay? Let's talk about LMT Onsrud, because LMT Onsrud, we started in that is not right. 1946. 1946. I have to change that later. But we started in 1946, not 1964. And we started in Chicago, actually. And then we moved to Libertyville, which is 8 miles from here. So here's 1946. Okay. So they started Onsrud Machine, actually, prior to that in Chicago. And then Onsrud Cutter Manufacturing in Libertyville in 1946. In 1999 is when Onsrud Cutter was bought by the German parent company, the LMT Group. So in 1999, we were part of LMT Group. Okay. Today we moved into this building in 2010. So we outgrew our space in Libertyville. We couldn't expand. We had railroad tracks, a pond, other businesses. We couldn't expand there. So we purchased this building in 2010, and we moved in December of 2010 to this building. So I can't believe we've been here 16 years, because I was in the other building too. But in this building, we're able to double our office space, double our production space. We also own the land next door to us, so we can actually double the building if we need to, when we need to. Okay, so like I talked about, we have a company of an international group with 100 years of toolmaking experience, 800 employees around the globe. Onsrud was a 3-time Challenger Award winner. Anyone, if you don't know what it is, you probably don't. But has anyone been to IWF show in Atlanta? You guys probably have. So this is like the largest woodworking show in the United States every 2 years. And they have, you apply for an award, and it's very hard to get the Challenger Award. We've won it 3 times. The last time was in 2016 on the Polaris compression tool, which we've actually phased out by now because it's 10 years old. So, we need to rotate some things through. Globally, we are in 13 service centers. We have 5 production sites, mostly in Germany and the United States. You see some guys here from LMT UK and the Czech Republic. Okay, so they sell all the brands and tools out of these offices too worldwide. We have customers in 43 countries. It's probably growing. We like to say that we can turn around specials. So most of our product that you'll find, most is in these 2 catalogs, but we sell about 20% of our tools are specials. So maybe a longer length, or overall length's a little longer, diameter's a little different, something different about it. And we can turn around those tools in 8 working days if they're coated, and 6 if they're uncoated. So we try to bring the technology forward. I went over this already. For you guys. Some of our leading industries we look at, besides like woodworking and like the sign industry and things like that, is aerospace, medical, and energy. Aerospace, we have a lot of composite tools for those, honeycomb tools. We have a lot of end mills for titanium, aluminums, and things that go into aerospace. Think about anything in an aircraft, like the overhead compartments. That's all made of composite. the doors, cockpit doors, the floors, the nose. Most things are made of composite. Medical, we do a lot of tools in the medical, like mostly like knee replacements and body part replacements. We have like a lot of plastic tools for that. We've got a lot of plastic tools for medical device trays, for operating rooms and things like that. Energy, the wind turbine blades. We've done tools for those types of things too. So not just what you think of cabinet shops and sign shops, but some of these other industries we're into. So like I talked about, wood and plastic, metals and composites. We focus on flexibility. Like I said, we do a lot of specials. So when Martin comes in here, he's one of our guys that does the special quotings, Martin and Bill, and Nick sometimes. But they try to turn around the quote, if we can, in 24 hours, unless we need to get some special blanks quoted or things like that. And we have a pretty good, hit rate of orders we get from our special quotations. And we have excellent turnaround time for them. Best in the industry. Some of the things we offer, we have an Encore program, which if you have a huge opportunity, our guys can go in and help make their program more efficient. They won't give them the program per se, but they will tell them how to program it more efficiently. We have our materials lab, which is where Gary is, our lab. So this is where you guys will probably find interesting is if you have some really odd material and you call in or you talk to your sales guy and they're like, ooh, that's weird. Can you get some material? You can send it to us as long as it's a big enough sheet or whatever that we can test tools on. We'll throw any of the tools we have at it that we think will work. It'll give you a report free of charge. Okay. So that may be interesting, if it's some very odd material. We do that all the time. And then training, where you're here now. For those who know Rob Cliff, that's him. So the Encore program, I told you some very large opportunities. We optimize the toolpath strategy with the tool geometry and machine capabilities. And the material labs, we talked about. You can bring your material here. We also do all of our new product development training in there, development work in there, etc. And training, we have worldwide training. This is the training we have here in the U.S., but we have trainings in Europe too. Usually there's around 4,000 participants a year. Not here, but worldwide. Okay. For those who order tools from you as one of your jobs, hopefully you have a login and password to our site where you can check inventory and place orders. We also have some larger customers going through EDI, and then we're on social media. We also have a university partnership. So we focus on the next generation. So here's our apprentices and their manager here. So we have a joint program with some of the local technical colleges and junior colleges here in Lake County, where the students will be in class some part of the day and be trained here on other parts of the day, or depending on how their class works, it can be some days on, off, or mornings, afternoons, or different shifts. So it's very hard to find people who know how to run CNC grinding equipment, and you'll see a lot of it out there. So we are developing our own people. So we recruit at a lot of the local high schools around this area in their technical program. So our HR manager in Delabar, who's this guy right here, spent a lot of time at local high schools and things like that. We bring some of them in for tours. We even invited their parents to come in for tours too. Because a lot of times you need the buy-in of the parent, right? Too. So these are our current apprentices. I think we have, 5 of them right now. So that's a big part of our recruiting and building that generation. All right, any questions for me? There's always a question that someone asks is CR Onsrud. How are you related to CR Onsrud? Anyone? Okay. So CNC is a CNC router manufacturer, which we have their router in our lab. We are totally separate companies, always have been separate companies. It was two different brothers started two different companies back in the 1940s. So one of the brothers moved to North Carolina and started LMT Onsrud, and the other brother stayed here and made cutting tools. So yes, they are a distributor of ours, like we are with a lot of CNC manufacturers, but we're not the same company. So that's always confusing for people. And why would there be two companies named with Onsrud, right? So. Yes.
You had said best in class, and I've run an Onsrud end mill doing something, and I've run an end mill by somebody else, and I can just tell the Onsrud with the same input criteria. The Onsrud seems to be in better shape at the end of an epic run. What would be just a simple heart of the matter? Explain what I'm seeing of what you just said. What is it? What is making it best in class?
Yeah.
Is it the material that you're using?
All of it.
Okay.
So we have a lot of experience. So we use different material. The carbide may look the same, but we use different material and different material grades according to what the tool is intended to cut, what material. So we are not using the same carbide to cut wood that we're using to cut titanium, okay? So we do a lot of testing to figure out what the best material grade is. We do a lot of testing on different geometries for that material. We perfect our grinding processes out there, because what you don't want a lot of jagged edges off the grinding that you may not be able to see with your eye, but you can see with your loop or something. Okay, so we've perfected a lot of different things. We spent a lot of time on product development, so that's why we're better. So there, you will find people that have a CNC grinder in their pole barn in their backyard, right? They're probably buying the same carbide and making the same for everything. And they don't have all the perfections down, right? That's the best way. Any other questions? Oh. Okay. Martin's going to be next, so I'm going to get him. But if you want to get a coffee or whatever, restrooms right here. We're not taking a huge break, but yeah. Oh, you don't have that? Okay.
And where did you say you want it all done? Pick the work out?
You can put it right here.
What's that?
Up here on the front.
Oh, exactly. Were you going to
Is it warm in here? What do you guys
What's that
think?
so far?
Oh, that's Stu.
Yeah, Stu.
Stu Natsky, yeah.
Get to take a look.
That's
Who's doing that? Greek.
That's Woody.
Yes, and
It is. Are you Greek?
Yeah.
I don't know the Olgos that are Greek.
yeah, it's either one or the other. People are like, oh, I know a bunch.
What part of Greece is your
But
family from?
northern. So I always say, I'm like, somebody came to do that.
My wife and I went to Thessaloniki
Really good.
year before last.
Okay, so my family is 2 hours.
So does Joe.
They used to be, they actually made a new highway over there. Like mountains. And prior to it, they were out on the side. And very distant. Are going around, you feel like a horror. Well, you just run around too fast. But it's nice. Did you guys like it? What,
So my wife is Greek. And
Oh, she is.
Her family, the whole nine yards.
so you understand this?
And when I had gone the last time, I was gone to Greece. Bill Clinton was Greek. And I was like, give me back home. This is too bad.
Yeah.
And they're from the Philippines.
Okay.
And we went last time, and I said to my wife immediately, if someone said I had to live in Thessaloniki for a year, sign me up.
Oh, yeah.
Sign me up.
Yeah, very.
I love going.
really.
we're always visiting.
No, it's a different time too.
Go there for a while.
Plus, like, I find, I mean, I'm always, we were not the family that would go there in the summer. Some families would go every summer. But I went when I was like under college. But when I was 14.
It's nice, like,
That was
once
like,
I know that.
that was really when I saw
It's
it.
like writing on a notepad.
Turns out
I
it's
loved
awesome.
it. I loved it.
I'm a big fan of it.
You know, it was awesome.
So you speak right now.
Yeah. I'm like, I'm born and raised here.
No, I literally just use it like a notepad.
Well, my parents are from Greece.
Backside.
First language is Greek, dancing,
You can
singing.
like, you can
all
put
that.
PDF
It was like little
files.
Greece.
So I put all our
So when I
text
went to
words in there, and you can just copy the original documents
Oh,
and stuff.
God.
It feels like right on the
This is the part that I miss her.
It's gonna be like, yeah, that'd be.
But it was funny because they don't go there. We'd be here. It's like, what are you? I went to Greece. They're like, oh.
And is, I mean, as long as you just organize the
They
folder.
say it in the,
Like,
what folder? They don't, they look down.
Because you cover a big territory. You got a lot of
Yeah.
cities. Oh, you can use like a section.
How's it in Greek?
How about that?
Greek's probably amazing.
It's pretty good. It's a, you can tell I know that, and I'm okay with it.
Yeah,
you know.
they may not know you're from America.
Yeah. Oh, they.
I know you're not from there, but
Yeah,
if your Greek is
Oh,
solid,
yeah.
you're in.
Yeah, yeah. So, but it was funny because like you could tell me I was in Greece. When we go to Greece, we were going I just wondered like, it looks great. So then I go 5 years later. Now I'm 19, and I am like, and now the world is around. Now you know the best of all your world.
Right accurately.
And I remember the Euros came out. You remember
And if you need to copy, let's say you
Oh,
already.
Yeah, the girl, yep. And at that
I run on
time,
one of
the
them.
dollar,
I normally hold it
like
down.
God were the days.
And then
So
put them back home.
So after.
now the euros and the dollars. Same. About so I remember I went to the oh, and there was like a few of us.
No,
Two were
so this is
born
all
in
for.
and I'm the one who's born in America. Oh, you remember? It's your money living.
It is, yeah.
Now,
But see, you
what
can,
happens?
you can
I
put
looked at
stuff
him
in
like,
there like no
I
problem.
never made money out of this.
No.
I go,
You
what I
can write through the
understand,
actor.
yeah, but I was keeping your ass too. Oh, like,
So,
I was like, did your batteries go up? The same as your station.
No, you're good.
All right, we're gonna start.
Recognize
And
any
that's what I was like, I'm proud of.
Yeah.
You know, but, different.
David?
It's definitely a different
It's gonna be
vibe.
fine. Okay,
This is
we're gonna start off,
It's just not
ready guys?
Ready?
John.
There you go.
All right, we're gonna start with the next section. So this is Martin, and Martin, want to do a little intro of yourself?
Hi, everyone. My name is Martin Trzynski. I've been with the company for 20 years. I just had my anniversary in January, so 20 years. I actually, I've been kind of all over the place. So I started in shipping back in 2006. I was there for about 6 months. I then moved out to inside sales. I was in charge mostly of international ordering. So I used to handle a lot of the international accounts. Did that for about 6 months, and then a technical position became available as a tech support and a coding specialist for custom-made tooling, and I've been doing that since. So it's been about 19 years since I've been doing that. So yeah, so that's me. All right. That's why I was trying to like look at some of the names and see if I recognize it because I do a lot of talking on the phone with distributors and but I'm gonna cover basics at first. So just kind of going over some of the basics, the information that we need to obtain from the customer to make successful tool recommendation. And then just kind of help you guys Get all the things you need, because oftentimes when it comes to end users, they give you very little to go by. So a lot of times they just say, hey, I need a tool. This is the machine I have, and I'm cutting this. But they don't give you the specifics necessarily of, the size of the parts they're making, the thickness of the parts. So they give you very little to go by. So this is just to kind of help you determine some of the things that you need in order to make a good tool recommendation. When it comes to routing, so the premise is that a cutting tool works because it is harder than the material being machined. So when it comes to routing or milling or really, any of that, the reason again why it's working is because the cutting itself, the tool itself needs to be harder than the material that you're cutting. And what it does is it basically will create a chip. So that's what you're always looking to do, is you're looking to see a good chip formation and good chips. You don't want dust, you don't want tiny little particles, because that results usually in overheating issues. So the purpose of a cutting tool is to form a chip and create a chip. Router tools are typically designed for higher spindle speeds and kind of a carving action. So again, that carving action is what produces the chip. And then again, when it comes to routing, usually it's all done in one cut, meaning when you're done cutting with the parts, they're usually good to go. So you can take the parts off the table and they should be finished. You shouldn't necessarily have to do any sort of secondary finishing operations like sanding by hand, buffing, or any of that. So the purpose of a router bit is the way it's designed is to give you a good clean finish right off the table. There's many different ways to make the cuts. I mean, this is just kind of like to give you an example. When it comes to routing, we're always basically doing light cuts and forming a chip. But obviously you have two different methods. So you can use brute force, using a bulldozer if you're taking down a tree, or you can use a chainsaw to make lighter cuts. And again, when it comes to routing, this is just to kind of put things into perspective. When it comes to routing, it's light cuts, forming little chips, or forming chips that are big enough to evacuate the heat with the chip. So again, router tools, you make many fast, light cuts to remove the chips from the material. Chip evacuation is extremely important, so you always want to make sure that you have a good chip evacuation, so you don't recut the chips, you don't generate more heat. You want to try to get the chips up and away from the material as quickly as possible. When we're talking about the chips themselves, we're always going to be talking about chip loads or chip thickness. Typically 5 to 30 thousandths of an inch is a typical range for chip load. Put that into perspective, so 5 thousandths of an inch is roughly like the thickness of a catalog page. 30 thousandths would be if you stack up 6 sheets of catalog pages. That's roughly what a 30,000 chip thickness is. So if you've ever looked in the back of our catalog where we have the chip load charts, like the cutting tool data information, you'll notice always numbers that start with like 0.005, 0.013, 0.015. That is the chip thickness. That's what we're referring to. And again, all the chip loads that we have will typically range anywhere between 5 to 30 thousandths when it comes to routing. When it comes to milling, sometimes they can be a lot smaller than that. But when it comes to routing, typically, 5 thousandths, 4 thousandths of an inch is like the smallest, and it can go up as high as 30 thousandths. I know some of this is irrelevant for the time being, but when Mike goes over feeds and speeds with you guys, like actually calculating feed rates and spindle speeds and chip loads and all of this is going to start to make sense.
Is it similar like a rice, like a normal rice? It's a bunch of places, chips out you can have?
Yeah, so I mean, typically, I do have some chips that I can kind of pass around if you guys want to see. Actually, just pass the box around here. So you'll see, there's some hardwood chips, composite wood. Composite wood would be like MDF, particle board, things of that nature. Hard plastic, which kind of looks more like sugar texture, versus soft plastics where you get like kind of a curdy long chips. So I'll pass some of this around so you guys can kind of see the difference. This is from a plastic drill, so when you're drilling, you get these long stringy chips, and then they kind of like fall off to the side. If it's being used correctly. So I'll pass this around so you guys can see what how the chips vary depending on the type of material that you're cutting. Again, so the purpose of this seminar, especially when we talk about basics, is just kind of give you guys the building blocks that you need and more like the information, the necessary information that you need to obtain from the customer to make a successful tool recommendation. And then we typically try to follow it in the same order, but it doesn't necessarily have to be the same. It just basically means get all the information that you need from the customer. We have it in order that we typically follow, but it doesn't mean you have to follow it exactly the same way. You can kind of switch it around. And then we'll have it on the next slide so you guys will see what that is. Because again, like I said, a lot of times we're working with very limited information. Very, very limited. Sometimes it's extremely vague. So you want to try to get as much detail as you can from the customer. And then so this is the information that we need. Again, you can change the order around. It doesn't necessarily have to be the same way. But the first thing we usually ask is always, what type of material are you cutting? Then we need to know the condition of the material. Condition meaning, is it soft? Is it hard? What is the actual condition of the material itself? Because that does make a big difference. And then what type of equipment they're using? Whether it's a CNC mill, a CNC router table, a hand router, something of that nature. So once we have the material, the condition, and the equipment, also when it comes to material, you also do want to find out what the thickness of the material is. Because you have limitations on the cutting length. So if it's a very thick material, then you know that you most likely you're going to be looking at larger diameter tools in order to support that cutting. So material, condition, and equipment. Once we have all those three, we will then look at the tool material that the tool should be made from in order to work for that specific material itself. The tool material would be high-speed steel, solid carbide, or PCD when it comes to routing. So you have high-speed steel tooling, which are very inexpensive. They were very fast, but they do have a purpose. So high-speed steel tooling is usually more for hand applications, not so much CNC router because of the flex. They give it flex too much. But the reason why they work in hand applications is because they are able to give and flex a little bit. So since you're pushing by hand, a high-speed steel tool usually will not snap on you or break on you. If you try to use a solid carbide tool that's designed more for CNC routing in a hand application, you may end up with a lot of tool breakage issues because it's just way too brittle.
Martin, is there any logic in using the less expensive high-speed steel tool when you're trying to figure out a approach to something and then go to the more expensive tools?
Not so much. I would say pretty much high-speed steel tool is only just considered more like a very entry-level tool, more for hand applications.
Right. Okay.
Pretty much always, if someone's doing hand routing, they should be looking at high-speed steel tool. Very little use in CNC, and I would say you almost wouldn't want to necessarily waste the time even using a high-speed steel tool because your choices are also very limited when it comes to high-speed steel tooling and the offering that we have.
Yeah.
It is just either a single flute or a two flute, and that is it.
Yeah.
And then you have an upcut or a downcut. But again, they're more of a general purpose universal tool. So some people use them for wood, they use them for plastic, in aluminum, but again, it's all just mostly hand application. If you try to use it in the CNC, again, not that you're necessarily wasting time, but it won't give you the finishes you need. It'll dull very fast. It won't be consistent because of the flex. So they do flex a little bit too much in the CNC environment. You won't be able to feed it very fast because again, it'll give and bend too much. So mostly just strictly hand routing operation.
Thank you.
when it comes to routing, typically it's going to be solid carbide. Solid carbide is probably 80% of the time. And then you have PCD. So PCD is a diamond tool. PCD stands for polycrystalline diamond. What that is basically typically you have a solid carbide body, and then you have diamond that is brazed, kind of like welded in a way onto the body itself. That's mostly used for extremely abrasive composite materials. So like Kevlar, carbon fiber, anything that has maybe silica in it. Very, very abrasive application. That's typically what we use PCB tools for. But so you decide on a tool material that you're going to use. Again, when it comes to routing, majority of the time it's going to be solid carbide. Tool geometry. So tool geometry, again, is very important. Mike is going to go over all the different aspects of the different geometries that we have. So we're just simply telling you that once you have the three basic things that you need for the material itself, you're then going to decide what do I want the tool to be made from, as far as solid carbide or PCB. The geometry of the tool, meaning is it a straight flute, is it an upcut, is it a downcut, is it a compression? I know some of these terms you guys may or may not be familiar with. Again, Mike is going to go over the different tool geometries that we have and why we use them. This is just kind of the building blocks that you need to make a successful tool recommendation. And we will go over the tool geometries. And then setup. Setup would be setting up the machine, making sure that everything's set up correctly, so your vacuum table is in good working condition. There's no movement. When it comes to setup too, it's always important to make sure that the sacrificial board that's on the router table, so the spoil board itself, that it's perfectly flat. The spoil board has a tendency to swell up or warp a little bit because of humidity in the air. So usually it's a good idea to resurface the sacrificial board as many times as you can to make sure that everything's 100% flat.
Is there a recommendation of how thick you need to have it? The board on the top of your table?
No. So usually, like the stuff that we just get it at the big box stores, Home Depot or whatever. So it's standard 3/4 inch thick material. But the very first thing Gary, who you guys are going to meet in the lab, the very first thing he does is he resurfaces both sides of the MDF because it'll most likely be warped a little bit. So he resurface the one side, flip it over, resurface the second side, and then it's good to go. And then he checks it every now and then. Usually if he starts to notice issues where the parts are shifting, moving, even though we have perfect vacuum, that's when you know that something is off. So maybe it's holding in one spot, but the MDF itself might be slightly warped in a different spot, which is why the parts are now shifting or moving, or don't generate enough vacuum to hold on to the parts.
So they take about 16 off the surface?
About a 16th of an inch or so they typically take off, yeah. So by the time you so if you start, you may be left with a 5/8 thickness once you resurface both sides. So once you have, again, the material, the condition, the equipment, you decided on a tool material, decided on a tool geometry, and then making sure that the setup is in good working condition, you would then usually move on to the calculations themselves. So you would go to the back of the catalog, look up the chip load recommendation for that specific material and that specific tool series. You then go ahead and do the calculation when we calculate the feed rates. And then the direction of cut. Again, Mike is going to cover the difference between what's known as a climb cutting method or a conventional cutting method. It does make a difference on how the chip is being formed when you use climb cutting versus conventional cutting method. It also affects the finish itself. So there are some materials that you pretty much automatically go to a conventional cutting method, let's say. And then there's some materials that you start off with climb cutting method. It just depending on the material, depending on the design of the tool. The tool itself, just so you guys know, the router bit or an end mill, it doesn't care whether you cut it in a conventional cutting method or a climb cutting method. The tool itself does not care. But the finish is affected and how the chips are being formed is affected by the direction of the cut. When I say the direction of the cut, I mean, so let's say if you have a spindle that spins in a right-hand rotation, you can come into the part and go to the right, or you can come into the part and go to the left. So that's what you have to decide on. Do I want to do climb cutting method or conventional cutting method? And Mike, like I said, will go over the differences between the climb cutting method and the conventional cutting method. And then startup and tune-up. So what we mean by that is once you have figured out your feed rate and the spindle speed and the direction of cut and maybe even the depth of cut that you're going to do, go ahead and start the machine, start the process. And then the very first thing you usually want to do is pay attention to what it sounds like and pay attention to your chip formation. And then if you can glance at the finish to see what the finish it looks like. So you want to see good sized chips kind of flying all over the place. You want to make sure the tool itself is not screaming, so you don't hear high-pitched noises or anything like that. If everything's running correctly, it should be relatively quiet. If something is screaming, if it's making a super high-pitched noise, then something's wrong with the chip or the feed rate calculation. So something is off. And that's usually creating more heat, which is why it's making that high-pitched noise. And then doing any sort of tune-up. So tune-up means optimizing what we call optimizing your feed rates. What we mean by that is that if everything's running good and you're getting good finishes, you could probably still improve on that. Meaning you could probably push the machine a little bit faster and still get relatively good results as far as the finish before the finish starts to drop off. That's to increase your production time, to get as many parts out of the machine as you can. So optimizing feed rates means once everything is running correctly, you typically would want to maybe increase the feed rate by about 5 to 10% faster, one at a time, and then observe your finish and see what your finish looks like. If you bump it up 10% and your finish is still good, go ahead and bump it up another 10% and see if your finish is still good. At some point, when you start to feed way too fast, your finish will start to drop off. So what you can do is when that starts to happen, you bring it back down 10%, and then that is your fastest feed rate that you can use with that tool for that material while still obtaining a good finish.
Does it go out the bit after a while? Faster?
Not necessarily. So all of the chip loads that we have in the back of our catalog are very conservative. Again, that's because we don't necessarily know the condition of the machine the customer is using or the vacuum table if it's in good condition. So we don't want to give you something that is way too fast right from the start, but we also can't give you something that's way too slow, because then that's when you start running into major overheating issues. So ours are just kind of a safe zone. It's a kind of a good starting point, but it's very conservative. So you can typically still go 2,000s, 4,000s, maybe even 6,000s of an inch higher chip load than what we have in the catalog. It's just kind of a more than point. But you're not necessarily worrying. You'd have to go extremely crazy fast to really use the tool. Exactly. So again, these are just some of the things that we need to get. So the baseline, the material, the condition, the equipment. Selection is you're going to make the tool selection itself, decide on the tool geometry, and then make sure that they have a good setup as far as your vacuum table, condition of the tool itself, condition of the collets, condition of the tool holders. Then you do your calculations, then you start the process, and then do any sort of tune-up or tweaking. All right, so next we're going to go over some of the different materials that you may come across when it comes to routing. If it's routing application, typically it's going to be wood, plastics, or non-ferrous materials, or composites. We don't have composites listed here, but so wood, plastic, non-ferrous metals would be anything such as aluminum, copper, bronze, things of that nature. Not titanium, not stainless steel, not steel. That's ferrous metals, which would be more milling application. Since this is a routing seminar, we're mostly talking about routing. This would be non-ferrous metals such as sheets of aluminum, maybe block of aluminum, brass, copper, things of that nature. So first up is going to be wood. It's kind of broken down into two different categories, natural wood or engineered man-made wood. So natural wood is then broken down into still two categories, hard or soft. Examples of hard would be oak, maple, hickory, ash. Soft would be pine, spruce, cedar, poplar. Majority of the tooling that we have, router bits that are designed for wood application, they're able to cut both, whether it's hard or soft. You don't necessarily have to pick a different tool. It is still the same tool, but the one thing that is different is going to be the size of the chip load itself. So if you were to look at the hardwood chip load information, the chips are going to be a little bit smaller. When it comes to soft wood application, the recommended chip load is going to be a little bit higher. And that's because with hardwood, it's more dense, so you're not going to be able to feed as fast. With softwood, on the other hand, you want to feed a little bit faster, because if you take your time and you go way too slow, you're going to generate heat again. Heat is like the biggest enemy of carbide tooling, because it's all chip cutter extremely fast. So you want the heat to be evacuated with the chip itself, not to stay within the tool and put it back into the part. And then typically that's the easiest one to spot, because you'll see it, you'll smell it, you'll see it smoking, you'll have burnt edges and all that. The second one is the engineered or man-made wood. So that would be anything such as, particle board, MDF, plywoods, melamine, like some of the stuff that you see at Home Depot or Menards. This is man-made stuff, so meaning it's made of fibers or wood fibers, wood particles, and then there's resin, glue, or something that is compressed into the material, making it into the material itself. When it comes to natural wood, so hard or soft natural wood, it's a fibrous material that is relatively easy to cut. So wood is a lot more forgiving as opposed to like plastic or aluminum. And then you'll see that a lot of times when you're routing. When it comes to wood, you can get away with having sometimes incorrect feeds or speeds and not see major issues other than maybe just a little bit of heat buildup. When it comes to plastic or aluminum, that window is very small, so you have to be pretty precise, because plastic has a very high tendency to melt, and with aluminum you have a high tendency to re-weld the chips. So wood is definitely a little bit more forgiving. Typically, 3/4 inch or less is what you're going to see for natural wood, but you can have much thicker materials, 2 inch or 3 inch. Anything that's usually up to 1 inch thick, oftentimes can be done in one pass. The much thicker stuff, such as 2 inch or 3 inch, will definitely will need multiple passes. And sometimes you may have to do a final finishing pass. What we mean by that is that if you're, let's say, have a 2 inch thick material and you're making 4 passes to get through it, to get through the thickness, if everything is running perfectly fine, you shouldn't ever feel the lines where you were stepping down, but it's a visible line. So you may see visible lines. So if you need to have a consistent edge finish and you cannot see the lines, it may be necessary to come back and do a final finishing pass. A final finishing pass means you're coming back usually with the same tool or maybe like a finisher, and you're going to go all the way full thickness at once, but you're just removing a tiny little skin. So you're not putting a whole lot of pressure on a tool, because you're just removing maybe 1/16 of an inch, maybe 30-40 thousandths of an inch. But you're doing it at a full depth to get rid of the line. Just kind of put that into perspective as far as finish itself on the edge of the material. So if you're looking for something that's equivalent to a 120 grit sandpaper when you're sanding with a machine, then it is necessary typically to use a solid carbide finishing tool in order to achieve that same finish requirement. A finishing tool is basically exactly what that sounds like. So it's more of a secondary tool that is just used for final finishing purposes only. So it's a tool that you come back with once the material has been already cut out, and then you remove a tiny little skin to get that ultimate smooth finish.
You have to change that to RPMs higher just to do that for the finishing?
Nope. The tool itself may need different feed rates, but the RPM typically stays the same. But the feed rate may be different because, again, it all comes down to the chip recommendation. You may sometimes be able to get away with using two separate tools. So instead of using a router bit to do all the cutting first, and then let's say if you're coming back with a secondary tool to do finishing, you can oftentimes eliminate using two different tools and use what's known as a chip breaker finisher. So a chip breaker finisher, what that is, it's a tool that is designed to be used as a rougher and finisher all in one. If you guys want to kind of see what that looks like, if you go to page, for example, if you go to page 59, at the top of page 59, there's a 60-300 series. That is what a chip breaker finisher looks like. So a chip breaker finisher has these little horizontal notches on the edge of the tool itself. I'll pass this one around so you guys can see it. So it has these little horizontal notches. They're called chip breakers. What's unique about that is, so let's just say if you have a 2-flute cutter, those chip breakers are not in the same spot on the opposite flute. So they're offset, they're staggered. And so that's basically what gives you that roughing and finishing design to be able to get a good finish. So again, that's to eliminate having two different tools. You can use a chip breaker finisher and it'll act like a rougher and a finisher all in one. And the finish may be acceptable to the customer, where you don't have to use two separate tools. And then the very last note says that sometimes we can use compression tools. They can be effective in some cases. A compression tool, I'll pass one of those around too in case you guys want to see what that looks like. I got one.
It could be needed if you need to leave some dust.
Yes. So, well, for the compression or the chip breaker?
No, the chip breaker.
So the chip breaker again is just kind of designed to be used as a rougher and finisher all in one. Usually, a lot of times used in plywood to get a good finish. Used in MDF particle board, but for that you typically use that tool. That's a compression cutter. Very popular. Chip breaker is extremely popular in hardwood applications specifically because what it also does by having chip breakers on a tool, you reduce a lot of the pressure or the forces that is on the tool itself, like the tool holder, the tool itself. So it reduces lateral pressure, the side pressure, by having chip breakers.
Yeah, but for example, sometimes I have to leave some tabs in order to don't lose the piece.
Oh, I see what you're saying. Okay.
If you use the two tools, with the second one you break the tabs, so you could lose the piece.
I see what you're saying. Okay. So yes, what he's talking about is sometimes if you have, so you're talking if you're cutting out a lot of parts out of one sheet, you're leaving like an onion skin on the bottom.
Yeah.
Kind of like just to make sure everything stays in its place and stuff. And then you're doing a final finishing pass where you remove that.
Exactly.
Do you remove usually off the side and the bottom a little bit?
Exactly.
Yeah. Okay. So I know we go over that in I think later today when we talk about routing wood. Sure. Yeah, we go over what he was saying is a lot of times what happens if you have a big sheet of, let's say, hardwood and you're cutting out lots of little parts out of the sheet. Even if you have good vacuum, occasionally you may have issues where some of the parts are shifted. So in order to prevent that, you leave a little bit on the side of the material and you leave a little bit on the bottom. It's called like an onion skin. You leave that so that all your parts stay intact and don't move. Then what are you doing where a majority of the material has been removed? So all the heavy routing's been done. You then come back and do a final finishing pass where you remove the side and the onion skin and hope that nothing gets shifted or disrupted by doing so. Because again, most of the routing's already been done, so all the heavy work's been done. You're just coming back and taking a little bit off the side and a little bit off the bottom. But the compression tool that I passed around, compression means it's both an upcut and a downcut in one. So as it's cutting, it's compressing, and it's giving you a good finish on top and bottom, as well as the side. Compression tools is like the #1 tool that's used for anything that's man-made, usually plywood, MDF, particle board, melamine, this kind of stuff, like the tabletops or desktops. So you have anything that's laminated, anything that has a laminate on top and bottom, in order to achieve a good finish and prevent chipping, typically use compression tools. So then the engineered man-made wood, again, things such as MDF, particle board, plywoods, things of that nature, melamine, anything that's man-made. What that usually consists of is having wood fibers that are mixed with resin and then compressed into certain thicknesses. The most typical is what you'll see is a 1/2 inch or 3/4 inch thick materials that come in big 4x8 sheets. But there are thicker. I mean, you can get 1 inch, sometimes you see, or 1.1 something like that. Typically, this is done all in one pass. And again, what I mean by that is when it comes to man-made materials, particle board, MDF, melamine, oftentimes you use the compression tool that I passed around. And again, the compression tool, the way it's designed to be used is usually all in one pass, all the way through the material. There are some compression tools that have what we call a mortise type compression tool. Mortise type means that it's got a very short upcut and a much longer downcut section on a tool. Those are the ones that are designed where you can do through cuts all the way through the material, or you can also do shallow channels known as dado cuts, things of that nature, and still utilize or maintain the upcut and a downcut of a compression tool. But usually, when it comes to these materials, it is all done in one pass, usually with a compression tool, to get the best finish on top and bottom. Plywood can be sometimes a little tricky because it is the one that's most dense, most abrasive, and it has the higher amount of resin in it. And what's also unique about plywood is that instead of having tiny little wood chips that are usually mixed with resin and formed into a material, with plywood you have layers, and then they are alternated in different direction. So you have one layer that goes in this way, then you have a second layer that goes that way. So they alternate in 90-degree direction. And that makes it more difficult because what you're doing is you're actually cutting with and against the grain. So you're cutting with the grain, and because of the other ply being flipped at 90 degrees, you're cutting against the grain. So it's a little bit more challenging to achieve a good part finish on the edge of the material with plywood, which is why for plywood, usually specifically, we use a compression tool, but what we add is we add the chip breakers. So more specifically for plywood, we use what's known as a chip breaker finisher compression tool. I know it's kind of a mouthful. So we have an up and a down in one to, again, help with getting a good finish on top and bottom. So it's pushing from the top, pulling from the bottom, giving you a good top and bottom finish. And then the chip breakers, the purpose of these chip breakers on a compression tool for plywood is to break up the chips into much smaller pieces and giving you a good finish. So again, because plywood is thin layers, not just tiny little wood particles, but actually layers of wood, you want to be able, it's a lot more dense, so you want to be able to break the chips into smaller pieces. And that's what the chip breakers do. The chip breakers help you make those chips into much smaller pieces, so it gives you a better finish. It also, again, because of how dense plywood is, it reduces the cutting forces on the tool. So, longer tool life, quiet operation. It's not putting a whole lot of pressure on your spindle or your tool holder, and wearing out the parts on the machine itself. So again, it's done usually in one pass because you're using a compression tool that typically is designed to be used in a single pass. Just a little side note, so plywoods have many different, we've seen many different qualities of plywood. So there's a lot of stuff that's coming from overseas, that's very inexpensive. It may have metal particles left in it, needles and all kinds of things. So it does make a difference on the type or the quality of the plywood that you're cutting. Baltic birch is what is considered a good plywood grade. But because of that, it has more plies, it has a lot more adhesive or resin, so it makes it a little bit more difficult to cut because it shortens your tool life. And chip loads, when it comes to chip loads, typically for hard plywood application, you're going to see smaller chip loads because you can't feed it as fast because it's a lot more dense. But it's what's considered a good quality material. You just kind of have to keep an eye on the tool life, make sure that you're getting the tool life that you need. Sometimes you can add a coating to a tool to help keep the cutting edge sharper longer. Those are just some of the things you can do with, for example, compression tools and adding a coating to a tool. All right, so next up is going to be plastic. This is probably the one that's got the most diverse category because there are many, many, many different types of plastic materials. It can vary between the hardness, the thickness. You can have variations from one batch to the next batch, meaning, let's just say if you're cutting a soft plastic such as UHMW, it can vary slightly from one manufacturer to the next, or it can vary from one batch to the next because they use chemicals, and sometimes if something's a little bit off, you may see some slight variations. Again, you'll see variations from manufacturers, so if it's coming from one company and it's UHMW, and then you get it from a different company, UHMW, sometimes they may work a little bit different. So when it comes to machining or routing the plastic, you may see slightly different finishes or how the tool itself creates chips, depending if it's coming from a different manufacturer. Even colors, sometimes the color itself can machine slightly different. So you can have, HDPE material that comes in black versus red versus blue or something like that. Sometimes even the color itself can machine slightly different. Again, it all depends on the chemicals that are being used in the material in the processing method. Cast versus extruded. So there's two different processing methods for making plastics. Anytime you see cast, it typically means that it's a hard plastic material. Extruded is soft. So, for example, what happens is a lot of times we get phone calls about cutting acrylics. The first thing we ask is, what type of acrylic is it? Is it cast or extruded? Because we need to know. Cast is hard, extruded is soft. So it definitely makes a difference when it comes to tool recommendation because we have different tooling that is designed for soft plastic or soft acrylic, such as extruded. And then we have different tooling that's designed for hard plastic or cast type material. The cutting geometry itself is different. So these are just some of the examples of soft versus hard. So some of the terms that you'll hear in the field is HDPE, UHMW, ABS, polystyrene, polypropylene, polyethylene, PETG. These are just some of the different names for soft plastic materials. Extruded acrylic again would be soft. Hard would be anything such as acrylic, but again, cast, not extruded. PVC. So PVC is a tricky one because it depends if it's expanded PVC. So expanded PVC is actually very, very soft. When we mean PVC, we mean like the very hard, rigid stuff that you find at like Home Depot Menards when it comes to like piping. So if it's brittle, it cracks and it breaks, that's considered hard. Nylon, Delrin, those are some of the examples of hard plastic material. If you have someone who is not sure what they have, there's a couple of different ways around it. So we can tell them to go ahead and make a quick little test cut and see what type of chip you get. So the chips that I passed around, if you get this sugar texture type, then you know that's a hard plastic material. If it starts to make a curly chip, kind of a long curly chip, then you know that's a soft plastic material. So then, choose, once you have that information, you can then choose the correct tool, make sure that you give them one with either the soft or the hard plastic kind of geometry.
Does it matter on the thickness and it's made of 3/4?
Nope. Yeah, it won't really make a difference. So whether it's quarter inch, half inch, three quarter, if you can just make a quick little test cut. We even say if you can take something blunt, you know, a knife, a piece of metal or something, and if you can easily make an indentation in the material, then that's probably plastic, soft plastic. If it's hard and it just kind of scratches the surface, but it doesn't really make an indent, then it would be considered a hard, a hard material. But usually you can just make a very quick test cut and see what type of chip you get. So that was plastic. Hard or soft does make a big difference. Again, wood is a lot more forgiving when it comes to plastic and aluminum. You really want to try to, nail down the tool recommendation and make sure that you're getting the proper cutting geometry for the material itself.
So, for example, if we're using a 1-inch nylon, would we use a chip breaker bit, or would you not?
No, so that's just more for wood application. So for nylon, we would use either a 1 flute or a 2 flute, what's known as an O flute. Again, we'll talk about geometries, but that's a good question. So I'm sure most of you guys have heard someone say O flutes, 0 flute, O flutes. It's a very common tool that is used in plastic and aluminum round. O flute simply just means it's the shape of the flute itself. So it's kind of it's shaped like a half moon design. It's designed to help you form a chip. It's what's known as a chip former. So it's help you form that curly chip. In a nylon, for example, if it's a thicker nylon material, the chip breaker that we passed around, that's just wood applications only. So that's just for wood application only. For plastic, you would typically use either a single flute or a 2 flute, and it would usually be a tool with an O flute geometry, but it's always smooth. It doesn't have any chip breakers on it. Even though it's a dense material, you don't need to break up the chips into any smaller pieces because these are the kind of chips you get. You need more of a smooth cutting geometry, but you need a geometry that is tweaked specifically for hard plastic material.
Kind of avoid less heat, basically.
Yeah.
Then would you actually switch the bit for finishing as you get that halfway down to at least about 3/4 minute?
Yeah.
Then finishing after that?
Perfect. So the other thing I was going to quickly mention about when it comes to hard and soft, the harder the material, the easier it is to machine. So the hard plastic, the hard wood, the hard aluminum, those are actually relatively easy to machine. Yes, it will have a little bit more damaging effect on the tool itself, meaning the tools are going to wear a little bit quicker when it's cutting harder materials, but you're not going to see major issues with overheating. You're not going to see major issues with melting or rewelding the chips. You're going to get really good consistent finishes usually in hard materials, and it's just a lot easier to machine. The soft material, on the other hand, is the one that's less forgiving, melts, rewelds like crazy sometimes, bad finishes because of, again, the melting issues or things of that nature. And so it definitely requires a tool that's designed specifically for a soft plastic or a soft aluminum or soft wood application. The harder the material, the easier it is to machine, and that's usually kind of, just to keep something in mind. Because, especially when it comes to aluminum, for example, aluminum can be very, very tricky because with aluminum, you could be saving yourself a little bit of money when it comes to purchasing the material itself. The difference sometimes is not that much between something that's medium hard or soft. So a lot of customers will end up buying soft aluminum applications, such as, let's say, a 3003 series aluminum, which is considered extremely soft and gummy, and it is a disaster to work with. It just revolves like crazy. It'll gum up the tools. You'll probably end up breaking or snapping a lot of tools. So when it comes to aluminum routing, again, the harder the material, the easier it is to machine. Usually anything that's in a 5,000, 6,000, or 7,000 series is considered relatively easy to machine. 50, 52, 60, 61 is probably the most commonly used type of aluminum. 70, 75 is more aerospace. So that's extremely expensive. The hardest type of material, but also relatively easy to machine. 2024 and 3003 series is what we consider soft. And again, a lot of sign shops will tend to use those materials because they're, saving themselves a little bit of money purchasing it, but then they're having a horrible time trying to run it. So we usually say if you can go to the 5052, that's the happy kind of a medium when it comes to aluminum.
Is that similar to like the material we have, it's called ACM?
Yes.
Half plastic, half.
Yes. So ACM, the aluminum composite material, like Dibond, Alucobond, and some of those materials. So you have a very thin layer of aluminum on top and bottom with mostly very soft plastic in the middle. That one is considered soft. We do typically use the same tooling that we use for routing aluminum for cutting that, or you can sometimes use a tool that's designed for cutting soft plastic material for the ACM material and get relatively good results where it's not melting or causing issues. So yeah, ACM is a very good example of a material that we don't talk about here, and we talk about it in a different slides. But ACM is considered a aluminum composite because you have a very thin layer of aluminum top and bottom with a soft plastic in the middle.
Do you recommend peeling the film off as you do the router, or leave it on?
So some people leave it on and they protect the surface, and you kind of have to see and play around and see what it does. Sometimes what happens, depending on the adhesive that is used for that top protective layer, the film, if that adhesive gets on a tool, then it'll start to create a mess. You'll have chips that get stuck within the flute, and then it becomes all clumped up. And then if it gets clogged enough, it can sometimes potentially break the tool, snap the tool, because you're then, you're rendering, you could basically eliminate the chip evacuation that is necessary for the tool.
Well, sometimes when basically you start to go from when you're cutting, you quarter inch spacing, and then you're expanding to the rack.
Correct.
Your inches not coming out, right?
Exactly, yes. So that's another thing too. If enough material wraps around the bit, you could potentially lose your tolerance on the material, and then your dimensions come out slightly different because you've got so much built up on the tool itself that it's no longer cutting true to size in a way. Another type of non-ferrous metal. So when it comes to non-ferrous metals, we have aluminum, copper, not as common, but you'll see occasionally people cutting copper, brass, bronze, things of that nature. Non-ferrous metals come in many, many different shapes or forms, whether it's sheets, plates, blocks. You can have extrusions. They come in many different shapes. There's different types of forgings, how it's casted or if it's die cast. Most common when it comes to routing, since we're talking about routing, is just going to be a sheet of a non-ferrous material. So, 1/8 inch, 1/4 inch, 1/2 inch thick sheets. Usually anything that's much thicker than an inch, it's considered a block. So we consider that more of a plate or a block of material. Condition. So we kind of already talked about this a little bit. So, hard and soft, whether it's wood, whether it's plastic, whether it's aluminum or any other non-ferrous material. Hard, it's kind of counterintuitive. It is actually, even though it's hard, it is actually a lot easier to machine, and it is a lot easier to form a chip. But it will be a little bit more abusive on the cutting edge of the tool itself. So yes, the tools are going to wear a little bit quicker, but it's a lot easier to work with. Harder material is a lot easier to get good consistent finishes, evacuate the chips from the cutting path. Sometimes you may have to use tools with multiple flutes for harder materials, which is why if you have a thick piece of plastic, yes, you can use a single flute, for example, like an old flute style tool. But if it's a thicker material and a hard material, then oftentimes we'll introduce an extra flute. We'll go to a 2-flute cutter. You'll be able to machine through the material a little bit faster. Sometimes more flutes will give you a slightly better finish, not always, but sometimes.
I'm sorry, back that one sentence up again. You'll get a better finish if
Sometimes in hard material, so whether it's aluminum or plastic or wood, if you have more flutes, every now and then you'll get a better finish. So sometimes you may have a much nicer finish if you go with a 2-flute cutter versus a single flute cutter in hard application. Not always, because again, the tools that we have are so material specific, so we don't really make universal tooling. I mean, yes, there are some tools that are what we consider universal. If you have someone who's not willing to buy multiple different tools for different applications, so if they just want one tool for everything, yes, we have some tools that are kind of a happy medium. But if you have tools, because our tools are very material sensitive or specific, whether you go to a single flute or a 2-flute, the finish usually is relatively good regardless. But sometimes in a hard application, if you go with an extra flute, you may get a slightly better finish and maybe not have to come back with a finishing tool. Soft, on the other hand, very gummy, soft, has a tendency to re-weld to the part or to the tool itself. Sometimes you'll see the chips are staying within the cutting path. So instead of being easily evacuated with your dust evacuation or just the geometry of the tool pulling the chips off, sometimes you'll see where the chips are left in the cutting path. Sometimes it may be necessary to come back and do a final finishing cut again to get a good edge finish. You get better tool life with the tooling itself, and that's because it is a softer material, so it's less abusive on the tool itself. A common issue is that sometimes the part itself being soft, when you're done cutting, it can slightly deflect or shrink in size. So it is common to sometimes see with soft plastic material, for example, where you're done cutting and it will actually shrink just a tiny bit. And so now it is no longer true to size or gives you the tolerance that you need. So that's something to take into consideration.
Is that a concern if it's kind of like a 3-inch material? You as you know, and how soft it is, it will go down and the big goes down and down, and most of the debris stays in it.
Yeah.
If you constantly blow it out.
Correct.
Sometimes it'll cause issue with that, or not?
Yeah. Yeah, it can definitely cause issues. We've seen where with soft plastic materials too, if you remove a lot of the material, it will sometimes start to lift off the table. It will bend, literally, because you've taken out all the strength that's left in the material, and it'll start to work too much. So that's a common problem too. So, there's a lot of different things that you can take into consideration. That's why sometimes doing a final finishing pass helps, because you take your time machining the material down, and then to make sure that you get it to tolerance because of shrinkage issues, it may be necessary to come back with a secondary finishing tool and then just finish to get to the tolerance that you need. So again, less forgiving, but easier on the tool itself. So definitely longer tool life with softer materials. And then when it comes to plastic more specifically, you can run into thermoform plastics. So these are plastics that are formed into some sort of a shape. For that, typically you use some sort of a robot. Sometimes you're using a hand-routed operation or 5-axis machine that is capable of spinning in different direction or having different axes to achieve and follow the shape of the part itself. Usually when it comes to formed plastics, we use what's known as a straight flute cutting tool. So it's a tool that doesn't have an outcut or a downcut geometry, it's just a straight flute. And that's because most of these parts that are formed into a shape, they're thin. And if you use a tool with some sort of a spiral geometry, it will have a tendency to flex the part. These parts are usually mounted on some sort of a jig or fixture. And if you try to trim some of the material off, because of how thin the parts are, if you use an upcut tool, it's going to have a tendency to want to pull it up and lift it. If you use a downcut, it's going to do the opposite. It's going to want to push it down, which is why we a lot of times use straight flute cutting tools for thermoformed parts. They're usually in a soft state, so usually it's a soft plastic material. Think of like bumpers on cars. They're usually a soft plastic operation. And again, when they trim the pieces, they're using straight flute cutting tools to eliminate any sort of flexing. You can have different thicknesses in different spots of the material itself, so that's very common. or sometimes you may have to use a tool with a much longer cutting length. So even though, let's say, the material may start off 1/8" here, there may be areas within the part where they step up to a 1/2 inch or a 5/8 for rigidity, or make that material stiffer in that one spot. So when it comes to that, you're again using straight flute style tools, but sometimes you may have to go with a tool that has a much longer cutting length to be able to have the necessary length to achieve a good finish in all the different techniques on the part. And then the one thing you typically need to be very careful with is scrap. Scrap really is, you have to be careful with that no matter what you're cutting, no matter whether it's a flat sheet or if it's something that's thermoformed that's mounted on some sort of a fixture or a jig, because scrap can become projectile, and then if it comes in the tool path of the tool itself, then it can break the tool, it can snap the tool, things can go flying, so you gotta be very careful, make sure that any scrap always has a safe place to fall into and not come into the cutting path of the tool itself. This is not very common at all, but every now and then you'll have someone who has such a soft condition, it's coming off of some sort of a heating element, so the materials is what's still considered warm. For that, typically we always use high-speed steel tooling. Why? Is because the high-speed steel tool is extremely sharp. It is sharp as a razor. It has a razor edge on it. So the only way to effectively cut a material that is soft, that is still in an extremely soft, warm stage, is to use a high-speed steel tool because of how sharp the tool is. And then again, of course, you're dealing with possible rewelding issues. And then lastly is equipment. So these are just some of the different machines that you can use when it comes to routing. Obviously, the most common, since we're talking about routing seminar, would be using a 3-axis or a 5-axis CNC routing table. But you can use milling machines, you can use robots, you can use machining centers, or something as simple as hand operation, air routers, hand routers, things of that nature. Again, for that, typically we use high-speed steel tooling because carbide may be slightly too brittle. We have customers that are using carbide tools with hand routers, but you have to be a lot more careful. The tool doesn't give or bend; it will disintegrate into pieces if you push it too hard. Any question? I think we're a little bit behind schedule, but you guys don't have any questions, then I'm going to hand you over to Brennan Guy. He's our VP of manufacturing. He's going to take you guys on a little tour around the shop. So you guys are going to need safety glasses, which Brennan's going to explain. And then you're probably going to need your headsets because it can get a little loud in the shop. So. Sorry, we're running a little late. I think this is. You just went late from the break. Oh, that's it. We're good. We always do.
This is the tool material. How to pick which material in which application is something that's pretty important. Although I'm going to tell you right at the beginning, most of the time you're going to be using solid carbide, 90% of the time, literally. There are 4 main materials that we make tools out of, that everybody makes tools out of. There are some more niche edge cases, ceramics, and things like that, but we don't offer them and we'll find them in many applications. We got high-speed steel, carbide tipped, solid carbide, and polycrystalline diamond. The abbreviations you can see. High-speed steel, it's for homogeneous material. This is steel. It's just, specially formulated steels that they use. There's lots of different types of them. Steel. Since we're grinding it from a solid, we can do sort of a lot of different forms and shapes. You can PVD coat it to increase the tool life or get more lubricity or other things. It's used mainly in woods and plastics when hand routing. Some of the geometries that we have, you can regrind the tools, but some you can't. Pricing. The reason you use high-speed steel, there are 2. number one, you're hand routing wood or plastic, and you're like, yes, that'll be fine. It's good for that. Number two is because the price is the lowest. It's the cheapest tools, commodity thing. You might use, 1,000 steel tools and just, I just want to pay a small amount for them to do that. So the price is low, but your wear resistance is very low. Your hardness is the lowest of all the different materials. Your toughness is high though, so it can bend a little bit before it breaks, which not all materials can do. Carbide tipped. This is actually carbide tip. We call it a material, but it's really the style of tool. It is a brazed tool. There's multiple types of materials that go into this tool. There's carbide, the tip, and then usually a steel body of some type. Probably not the same type of steel as the high-speed steel tool. It'll be something less. We don't need it to be as hard. We don't need it to be as nice. Made by brazing the carbide tip tools to a steel body. It has the advantage of having a little bit of flexibility in that body, but higher hardness in the tip where the tool is interacting with the part. So you get the best of both worlds there. We can make it into really large shapes, complex shapes, yes, to do like molding or the edges of things like that, but only straight, only in like maybe a little bit of up shear or down shear, but only flat. So the price is going to be a little bit higher than a regular steel tool. Only steel, the wear is going to be higher because it's carbide, but in general, not the best carbide. So you won't get quite as good as you do from like one of our standard solid carbide tools. Toughness is sort of that amalgamation. The edges aren't going to be as tough as the steel tool, but they will last longer because they're harder. But the body does flex a little bit, so you get a little bit more out of it than you would a standard solid carbide tool. I say standard solid carbide tool because it's the vast majority of what we make and what everybody in the industry uses. It's sintered powdered material. So instead of being a poured steel, it's a bunch of particles pushed together really high, really hard, and under a lot of intense heat, and then ground to size. Tungsten carbide with a cobalt binder is what we use here. Most everybody in the industry does, but there are other types of carbides that you can use. Is many, many different grades, many, many different suppliers. We do all the work for you guys and do all the testing internally to find what are the best grades for different applications, and then we use that. Again, just like a high-speed steel tool, it's solid, so we can grind it into many different forms. We can do upcut, downcut, helical, different types. We can do up and down the same tool. We can do round flutes or B flutes or anything we can do. We can PVD coat it. We can also, certain grades, CVD coat it, which is diamond coating, so we can make it last longer in certain applications. It can handle higher chip loads than steel or carbide tip. We can do a lot of stuff with solid carbide. That's why it's the most common. The price goes up again. The wear ability for it to resist wear goes up over the carbide tip because we use better carbide, and the geometry allows for us to do that as well by fine-tuning that for application. But the toughness goes down. The high hardness of the material means that it will fracture rather than flex. So it'll just break in half. Failures in solid carbide aren't, my runout changed. That cannot happen. It will just break. And it has a high hardness of 3. Polycrystalline diamond, we're talking about the top 5% here. Again, we're looking at the same sort of geometries that we can do with carbide tipped, although in general much smaller diameters. Because of the cost, polycrystalline diamond is diamond. It's a manufactured diamond, usually with a carbide backer, but not always. And there's a lot of different grades, again, with this for different applications. It's always expensive. So you don't want to use big, giant chunks of it. In fact, you can't get as big as you can with carbide, with like a flat carbide tip. But we are limited to those flat-faced geometries. You can make it into complex forms, though. So weird shapes or molding shapes or thread shapes. Do all that stuff with a polycrystalline diamond tool. Super useful in hard, abrasive, or difficult to cut materials. Super useful in super high running materials. So if you're doing 10,000 pieces and you never want to change your tool, PCB might be able to do that for you, depending on the applications. The thing you're going to look at, you can't actually achieve the high chip loads that you can in a solid carbide tool because we can't make the geometry into a form that will do that. So price is the highest, wear resistance is the highest, hardness is the highest, toughness is the lowest because it is so hard it will fracture very easily. You don't want to try and do interrupted cuts or super anything where it's going to hammer or vibrate. And you can't do anything that is ferrous. Anything that is any steels basically just can't do it. It'll chemically react with it and it'll just blow up. So here's a chart for comparisons of this. You can see high-speed steel is like cheap, tough, good to go. Carbide tipped, a little bit better. Solid carbide, a little bit better. Polycrystalline diamond better. And then but backwards in terms of the toughness. How do you choose a tool? The harder material that you're trying to cut, the harder tool that you want. So that you can have abrasive against abrasive. The more abrasive the material, the harder the tool material you want. If you're cutting, carbon fiberglass, it's not very hard. It's not like, hardened steel, but it's very abrasive because it has all the other elements in there, thin strands of fiberglass or carbon fiber or something else that will just wear against the tool material. So you want the hardest that you can counteract that. Hand-fed applications, you need tougher tools because the CNC machine I can program to come down and move exactly this rate and it will do exactly what I tell it to do. If I'm doing it by hand, I can just use my own, this is about 12 inches a minute, or is it 100? I don't know, it's something around there. So the rule of thumb, anything that is on a CNC machine, solid carbide is your first go-to. Anything is a hand operation, high-speed steel is your first go-to. That's really the rule of thumb. If you're trying to do something that is hand operation, in most of the time, you want steel. You want the extra toughness, but it's just not going to last that long. But you can just change the tool out and be cheap, so that's a good thing. If you're going to be doing something on a CNC machine, you can program it in and not changing that tool for a much longer time and have being to go faster and be more consistent is going to have better implications. The only time that that's not true is sort of if you're looking at a price versus cost. So in the event that you're doing the same thing over and over again and you have a really good process set, you might want to think about going to a PCD tool because the longer tool life means less tool changes, means lower price per part. So even though you might be able to go a little faster with solid carbide, if in the right application, a PCD tool might be better for the long run time that you get from it. So yeah, what you pay to use the tool is the price of the part combined with the work center values and the time values. So this actually will be the main thing you're looking at when you're doing like setup and tune-up. If you're using a carbide tipped tool and everything is just fine, and that tool costs $50, then you don't want to pay for the $100 solid carbide tool, but the $100 solid carbide tool can get you a 50% increase in feed rates, which means that your time to make your part is 3/4, then it's more advantageous to use a solid carbide tool that costs $100 and get 50% more parts than to use the cheaper carbide tip tool, have to pay a new one every once in a while and get fewer parts per hour. Okay, any questions about that stuff? Just basically high-speed steel carbide tip, solid carbide is your main go-to, and polycrystalline diamond in certain situations. Yes?
Yeah, just a question. When you said that if you have to make something like 10,000 pieces, you have to choose between the solid carbon sorry, the PCB instead of solid carbon, right?
Maybe.
Okay.
It's more complicated than that because it depends on the exact application. That's why we always are like, hey, these are the main things. If you have a question like that, you might want to reach out and ask specifically, here's what we're doing. Because, as I said, you can't use it in steel. So if somebody's cutting steel, you can't use PCB. Just across the board, that's not going to happen. If you're doing something where your feed rates are super important, where you need to go really fast, PCB might not get you to that higher thing. So then it's a question of, is it better to go a little slower but have the tool last longer, or is it better to go faster and change the tool more often? So more factors than just that. But in general, yes, if your customer has a transfer line drilling holes in aluminum, you're going to want a PCD drill because you won't have to change it. And it's just going to be better for a longer period of time because the setup on that transfer line is going to be very heavy. If you're doing, if you're routing aluminum sheets on a CNC machine and the changes all the time, and you might do something, the risk of breaking that tool or something going wrong is high enough that maybe you don't want to do PCD tool because $1,000 tool versus $100 tool. So I get 20 times as many pieces, but if I crash it, it's gone. It doesn't matter. A $100 tool, if I crash one, I'm mad, but I'm not. It's not the end of the world. So we have to consider all those things.
It depends, yeah.
Yeah. Okay. Tool geometry. I'm going to pass out some 3D prints here, so for you guys to look at just for fun. As I go over geometry, you'll be able to see on there exactly what we're talking about, but in a three-dimensional version. Tool geometry serves three main functions.
It's actually
Cutting the chip from the part, removing the chip from where you're cutting it, and reducing that usable surface on the part. Tool geometry is what removes material from your part. We create that tool geometry by removing material from our part, which is the tool. All subtractive manufacturing, where the examples I passed out were made by additive manufacturing. Hey, we're using all the types of manufacturing today. We machine them on our grinding machines, which I think you already saw. You did a tour. You can also, with carbide tipped or steel tools, sometimes we grind almost exclusively. Some places they'll mill tools, mill the body for a tool before they put a carbide tip in or something like that. After we grind them or they are machined, there are next operations as part of that. We might grind or turn steel in the soft state and then send it out for heat treating because we don't do heat treating in-house. And then it'll come back and then we grind that. Or we do a brazing operation on a carbide tipped or PCD tool. After that, we do like finish grinding. So edge preparation or lands on the edges or different other things like that. Put coatings on, send out for different coatings, all sorts of different things that we can do to complete those tools. The main parts of tool geometry, the important stuff that you should need to know. Raking clearance, for sure. Helix, for sure. Flute fade out because people will get it wrong and we don't want that to happen. All the other stuff isn't just good enough, I guess. So the rake is the edge angle on the front of the cutting edge, which attacks the material and starts that chip form. That's the inside sharp bit. The clearance is the outside sharp bit. We grind it a little down so that it doesn't rub on your part. We grind at different angles depending on what the material that you're cutting is. Because sometimes you want it to be relatively close to your part, and sometimes you want it to be relatively far away from your part. Depends on the material. Together they make the wedge angle. No one's ever going to ask you about the wedge angle or tell you about the wedge angle. It's just the complementary angle that comes when you have a rake on this side and a clearance on this side. So with the examples, did everybody kind of get what the rake face of that is? It's the inside part on either the down cut or the up cut. That is the sharp. We change our rake and clearance based on materials, but there's a range in every one depending on the geometry we use. So if it's like a straight O flute versus a helical O flute versus a V flute, all those things sort of change. But in general, higher rakes in plastics with lower clearances, and in woods and aluminums, we have lower rakes with higher clearances. The helix is the angle that the flute twists around the central line of the body of the tool. It can be up or down, depending on which way it spins. We use the right-hand rule. So if it's right hand, that is an upcut. If it's left hand, that is also an upcut. Yes, it has to be the same. It's backwards. So if you're right hand, left hand helix, that's a down cut. If you're left hand, the right hand, the helix, that's a down cut. If they match, it's an upcut. I'm sorry, I have to amuse myself somehow, don't I?
Yes.
So it controls chip flow for chip evacuation, for part stabilization, for better edge finish. So an upcut flute, the chips flow towards the shank of the tool. If my tool is coming down at the table and I have an upcut flute, they're coming towards the shank, I'm moving my chips away from my part, which is advantageous because heat is what makes tools wear. It's what creates re-weld onto your part, bad finishes. Moving the chips away, which is where we try to concentrate all the heat when the cutting gets done, because cutting is a friction activity which generates heat. So you want to get that heat away as quickly as possible. If you're using an upcut, you're going to do that. It's going to come away. Part stabilization, a down cut, where we're pushing the chips down, not generally good because we're pushing the heat back into the part. Except in situations where that part might move on us, or we have, like when you have a finish requirement along that top edge, then we're not moving things past it. We're pushing into our holding. It's going to help us with stability, with part stability. Really, we want to do that with really thin materials. We'll get into that more later. Better part edge finish. Helical tools tend to create better finish on the edges of parts when we cut them. For multiple reasons, but we'll, again, address that a little bit later. So it applies force to the parts and the fixtures. When we have an upcut helix, we're pulling the part up. We're pulling the chips up, but we're also pulling the part up. We're touching both at the same time. So that we have to have really good holding for that. Down cut is going to push it down into the table. A straight flute, which has neither up nor down helix, will just push everything sideways. Everything is always being pushed sideways as well. I don't think I mentioned that. Whatever your direction of cut is, you're putting pressure on the part to go that way, so you have to have something to hold it down. In most cases, that's going to be vacuum, but you could screw parts down, you could clamp them down, you could have stops at the edge of the table, however you might want to do that. Flutes. Flutes are the inside face. They're the empty part that we create by grinding away material. That's where all of the chips go. So we want flutes to be really big so the chips can go in and they can move a lot of parts out so we can go really fast. But we can't make the flutes too big or the tool will be weak. We also we have to worry about how the rake is going to be created by doing that and a lot of other factors. So it's more complicated, but those are the flutes. We always call them flutes. They force the material on the chips. After the tool edge cuts them, the rake face cuts them off. They take the chip away from the cutting action. Tools can have multiple flutes. Single flutes are most popular when routing plastic and aluminum sheets. Multiple flutes produce better finish in most materials, and two flutes are the most popular in wood. All those things are true. I don't know why I say it. All right, let's talk about geometries in terms of flute shape, which we have gone into a little bit, but now we're going to talk about more in depth. Straight flute, no helix. Also PCD and carbide tip, exclusive, have to be straight flute. So we can see here, this is a carbide tipped tool. It's straight. We have a different, and this one are PCE tools. You can see they're different colors. They're different materials. We also have straight flute high-speed steel tools and straight flute solid carbide tools. Short shipping materials, they work really good. Plywoods, MDFs, hard plastics, stuff that when you cut it, there's little dust. Let's show some examples. Here's some hard plastic chips. Let's see what else we got in here for examples. Here's some hard wood. This would be good too. Plywood.
Oh, I'm sorry.
Oh, composite wood. Here's some composite wood, so you can see as well. Really short, tiny chips like dust. Straight flute tools are going to work well in these materials. But the straight flute makes a line contact with the part. Every time it rotates, the part comes in and it just hits. It hits all along that edge all at the same time. Maximum amount of force on that part, maximum amount of side force. No up, no down, just side. So you get sort of lines, you can get lines on the side of your part, depending on your speeds and all this other stuff. If you're banding it, if you're sanding it, that doesn't make any difference at all. So we're fine. In fact, on this one, it's got a rougher edge, so it's going to leave a rough pattern on the side of the tool part anyway. You'll have to finish that in some way if it's a displayed part. It's inside of a couch. No one's ever going to see it. Leave it rough. Here's another straight flute geometry. Oh, thank you. But this is a straight O flute instead of that straight V flute, we call it. Because it because it looks like a V. O flute because it looks like an O. It has nothing to do with type of material or anything like that. It just looks like a circle. Straight O flutes are used mainly for soft materials. So soft plastic, got that. That's this here, and then there's this big bag of black plastic. That's soft plastic too, a different type. Soft plastics, super thin plastics, super thin aluminum sheets. They are pretty strong tools, especially when the cutting diameters are really small on the shank. And it creates a lighter pressure on parts than the V flute straight, because they always have a higher rake angle. On V flute tools, rake is created by being off of center. So as it rotates to center, that creates an angle. Does that make sense to everybody? So I'm here, I rotate to center, now I have an angle here. If I'm here and I'm at center already, I have no rake angle. My rake angle is 0. On O flute tools, we can be at center and have rake at the same time. So we can create sharper tools. So for things that are very thin, light, that might pull up or get messed up by having an upward pressure, these only have side pressure. Good for soft materials.
How thin is aluminum can you go? Like the 016 to 093?
I mean, I've seen 10 thou thick aluminum sheets. So, you know, they call it mil, like 1 mil, but it's not millimeter. What I call it mil. So yeah, in composite materials where you have like plastic in the middle and then a thin layer on the side, like ACM panel, but with a thinner aluminum, you might want to use something like that because it won't pry the parts apart, and the aluminum is so thin that it's going to cut better with a sharper poke.
So it'd be less vibration on it.
Less vibration. It's only one direction. That's only pushing sideways, so you don't need to worry so much about having it pulled down. But you don't want to use a down cut, because if you use a down cut, it will be thick. In situations like that. Or if you just had a really thin sheet of just straight up aluminum. But in that case, you might get off the down cut. depends on whether you keep it cool enough by feeding fast enough.
So basically, do a lettering,
Mhm.
then you go air with the lettering.
Lettering, either a straight O flute or a down cut, depending on your exact application. Standard spirals. Standard spirals just have usually it can be 1 or 2 flute, a bigger core diameter, which is the center of the tool, or strength, but it means there's less flute space for chips to go. But they're recommended for materials that form curled chips, such as aluminum, pine, or poplar. Because it has a helix, because they have helix, they're touching at point to point. As they spin, they're sort of moving up the part. The forces are acting by moving up the part. Because it's only cutting a little bit, then moving, and then cutting a little bit, then moving and cutting a little bit. It's not a line action. It's not hitting all at once. It's hitting on an angle as it moves forward. So that's a little less pressure on your part in the sideways direction, but you're either pulling it up or pushing it down. Your total force is always going to be about the same. You're just changing the vector. It allows the chips to be directed either out or into the cut path. Down cuts can assist in holding the part in place, and generally smoother finish out of helical tools.
The other one, can you use that as a pocket, as a plastic, or that one?
This one, which,
That's what I am.
oh,
Can you do like pocketing out of it?
you can do pocketing you can do pocketing with an O flute too. Like none of these will keep you from doing pocketing. They all have points that will cut on center, so you'll create a decent. I mean, ones that have a point that looks like this don't create a good of finish as ones that have a point like this or this. But that's, you can use. You generally want to do your right upcut tools to do pockets because you're not recutting chips because it'll pull them out. But if you have proper like air blast or something on it, either one will do. It just depends on how you set it up. Spiral O flutes. This is getting more into what most of our stuff is. A much bigger flute shape in here, if you notice. We can take a bigger chip, we can move more chips, we can go faster. Anytime you can move more chips, you can feed faster. Feed faster means lower cost per part, better for your customer, more output. Spiral flutes are recommended for soft materials, UHMW, which is ultra high molecular weight polyethylene, high density polyethylene, Teflon, aluminum, acrylic, both cast and extruded acrylic, but you want different tools. They're called acrylic. If it's cast, you want a hard plastic tool. If it's extruded, you want a soft plastic tool. That's just the way the science works. Most popular series for plastics and aluminum. 63600 for aluminum. This is a 52700, which is probably the best tool in our catalog. 52700, write it down, use it for everything. But there's also I think this is a cast acrylic tool, which can do either cast or extruded acrylic. The 65000 series, high polish, is like sort of the workhorse single flute upcut. You can use that across a wide range of materials just by varying the speeds and feeds. Sort of jack of all trades, master of none. And then 63700 is a soft plastic upcut. 63750 is 63700 is a hard plastic upcut. 63750 is a soft plastic upcut. Just depends on the material. The most important thing you can get from your customer is what material are you cutting, because that's going to tell you how to tool select, what tool you're going to want. The second most important thing is how are you cutting it? By hand, on a CNC router, what are the expectations? How are you holding your part? There's lots of stuff, but the most important thing is what are you cutting? You can't start anywhere else. Upcut spirals, upcut pulls away from the part path. It assists in dust evacuation and removing chips from the cut. It'll keep your area cleaner if you use an upcut and have good vacuum, good evacuation vacuum. But it pulls your part up. Down cut pushes your part down. So if you need super clean top edges on something, you want a down cut, but you're going to be working against pushing your stuff down into your cut again. So with wood, not such a big deal. With plastic, you're probably going to start re-welding. So rake face, clearance face, this whole thing is the flute. This is a down cut because it's pushing the part down. And can we see that as it rotates? It's going to hit here, and then here, and then here, and then here, pushing the part down. These parts are upcuts. So it's the exact same thing, but it's going to hit here, then hit here, then hit here, then hit here. It's pushing the part up. This is a compression tool. We make compression tools for wood and composites. We have this area in the middle where they overlap, where interactions happen, and you get, I think, everything like that. But in general, we're pushing the wood parts down into the part. We're very clean at top edge, really great. If you use this in plastic, it would create a mess because we're pushing hot plastic back down. We're recutting it with the bottom. We're pushing it back up again. It's going to be real bad. So downcut's great. We need to know where to use it. Very shallow cuts, very thin parts, or in specific materials. But it does hold your part down part. Wood compressions is what I just talked about. Laminated wood, plywood, anything that can peel apart. Very great to use compression because it pushes the top down, pulls the bottom up, keeps everything together. Wood roughers. Wood roughers theoretically cut with less pressure, but they leave a rough finish on their part. Really only good in foams, woods, some composites. We stagger our pattern. So the pattern of the edge goes like up and down and up and down and up and down. We stagger that from one flute to the next. So you only get half of that depth. So whatever depth is on the side of this depth right here, you only get half of that because the other side, the peak will be in the middle where the trough is. So it's not as bad as it might look on the edge, but it's not going to leave a smooth side. And I will say, just between you, me, and the guys out in the shop, they do very little for reducing the actual thrust pressure that you need. Maybe if you're very close to an edge, this could do something for you. But in most cases, just using a sharper tool will get you better results than moving on to a rougher. Chipbreaker finisher, same idea, where we're not cutting, we have a little bit of release of that pressure every once in a while, but because we put the chip breakers staggered, you get a smooth edge still. Better than a rougher. Still doesn't reduce pressure that much, but maybe. It does leave a good finish, so in my opinion, better than a rougher, maybe a little more expensive. We do have upcut and downcut and thinner core than the standard spiral, so you're going to be able to run a little bit faster because we can clear chips more.
Do you see guys running those for chip management?
I do see people running chip breaker finishers and roughers for chip management purposes.
As
a chip management,
I've used them.
Yes, as a chip management thing, yes, to make it easier for your vacuum to pull the chips out, or if you're getting big piles and you need something to help ameliorate that.
Yeah.
That's when I would pull out a rougher or a chip breaker finisher.
For cutting pressure, they do almost nothing.
Almost nothing. With more cutting pressure, finisher, very low helix, either upcut or downcut, but 3 flutes, so it's gonna cut harder, but you're using it for finishing purposes. You're gonna cut it mainly with something else, and then finish with this tool by leaving 10, 15, 20, 30 thousandths of an inch on the side of your part, and then come back with this. It's gonna leave you a better finish because you got 3 flutes all kind of hitting on a little bit of an angle. It's going to be higher pressure, but it will give you a cleaner, smoother finish. Woods and plastics, upcuts and downcuts. You can use it in cast acrylics, which is a very interesting thing. I've seen people use it just to straight up cut cast acrylic, solid.
So actually do a nice finish that you can flame polish it without having the stretch marks in it.
Yes, we also have a polishing tool which uses PCD to finish acrylics, cast extruded acrylics or polycarbonate. It's not quite as good as flame, but it's repeatable. So you can, if you have a tool changer, you can cut with this or with a 63-700 or whatever, and then come back with a finisher 75-100 series and create an optically clear finish. Like you can put it down on something and read through it, but you can, it's not perfectly smooth like a flame polish.
Yeah, sometimes we have a lot of elements.
Yeah.
His plates.
Yeah.
I think that's basically sitting in his plate, backed up, not showing the stretch mark.
Yep. So yeah, if in situations where main problem with flame polishing acrylics is getting symmetrical to that, then you're going to get more failures. Where if you're using a CNC tool, assuming that everything's set up right, you know, nothing changes, it'll just be the same every single time, which is nice. Just something to keep in mind. We also make a lot of specialty tools. Not only specials, which we have a quote for you, and we have some of the best lead times in the industry, but out of the catalog of specialty tools, thumbnail radius, route and chamfer at the same time, bottom finishing. This is super good bottom finishing. If you want to use a pocketing tool, this is the tool. It's 60. Bear with me one moment. I can't remember. Out of my head. Uh, 66.
Was dinner good last night? Where'd you guys end up going? City Works, I think. City Works.
Well, that's, you know, I thought, oh,
I'm gonna start kind of where we left off. So, the last thing we talked about was this one. This is the chipbreaker compression tool. So this is the one that is more specific for plywood routing. Again, it just kind of helps up break up the chips into smaller pieces. It reduces a lot of the cutting forces on the tool because of how dense plywood is. So this is a great tool specifically for plywood applications. When it comes to engineered wood, so MDF, plywood, particle board, laminates, typically as far as the cutting method, we usually use conventional. You know, it's normal to see high feed rates. So again, with a lot of the tooling that's designed specifically for engineered wood, such as the particle board or MDF, most of the time you're using either compression tools, you're using chip breaker finishers, or you're using the compression with the chip breaker. So all of that tooling is designed for extremely high feed rates. Again, just kind of take that into consideration when you're making the choices or calculating the feeds and speeds to make sure that you're you know, giving someone something that they can actually physically work with regarding the size of the parts and all that. So again, larger chip loads, the chip loads for these tools are pretty high. And the larger chip loads definitely lead to better tool life. Again, heat is the biggest enemy of carbide tooling. So if a chip load is too small and these tools are designed for very fast feed rates, if you run it too slow, you're gonna you know, sacrifice tool life. It's gonna introduce too much heat, you know, burn out the tool, you know, way too quickly. So then again, next slide is going to be, you know, picking a tool, doing the calculations, looking up the chip load and all of that. So let me just kind of jump back and forth. I just want to see which tool we are choosing for this, which is on the assembly compression. All right, so the tool that we're going to use as an example in this is going to be the 60-123 MW. MW is the basic entry-level compression. That's a 3/8 diameter with 2 flutes. So again, here, same kind of scenario as with natural wood, meaning if it's a kind of a new user who's not used to, you know, doing a lot of routing, pretty much always we're gonna start at the baseline. So just like we did with hard and soft wood, which was just a basic general purpose wood route. In this case, we would just put them in a base, kind of an entry level compression tool. So the one that's called the Max Life or the MW series. For someone who's a little bit more experienced, the Marathon compression, which is simply a coated version. And then obviously if you have any HPL type material, like high pressure laminates, you definitely want to use the Endurance compression, because that is really the only tool that is going to have sufficient tool life in high pressure laminate. Tube flute is okay to use as a starting point. We don't see a lot of people using 3 flute compressions, again, because of how fast you would need to feed those tools. A 3 flute compression is going to put you over 1,000 inches a minute, which is incredibly fast. So very few people can use a 3 flute tool effectively without, having issues with feed rates and all that. 3/8 diameter is typical for a standard 3/4 inch thick material. You can go to a 1/2 inch as well. 1/2 inch is going to gain you a little bit faster feed rate, being a slightly bigger diameter, therefore the chip load is a little bit bigger. But 3/8 usually just as a good starting point, which is why we're going to be using the 60-123 MW, which again is a 3/8 diameter. So if we were to look up the chip load, so we have the diameter at the top, which is the 3/8, the 60-100 MW series, which is the series that the tool falls into. So it tells us that the recommended chip load is 19 to 21 thousandths per flute. Again, it is a 2 flute cutter. RPM wise, in this example, we're using 18,000 for the 3/8 diameter tools, slightly lower spindle speed, 16,000 for 1/2 inch tools as a recommended spindle speed. Again, really depending on the overall shape and size of the parts. But in this example, we're going to use 18,000 RPM. So if we plug it into the calculation, ship load times the number of flutes times the RPM. So we have 19 to 21,000 ship load. Just a side note, we typically automatically jump to the higher chip load when we calculate feed rates. You can either do the low and then the high and give yourself kind of a range. We usually say just go straight to the higher chip load. The reason why, again, is because our chip loads are very conservative without knowing the condition of the machine and all that. So we go a little bit on the slower side, not to the point where you're burning things up or prematurely wearing the tools out, but kind of a safe zone where you're not going way too fast. So it is okay to go ahead and use the higher chip load right off the bat. So we're going to use 21 thousandths times 18,000 RPM times the 2 flutes. So we come out with a feed rate of 756 inches per minute, which again is actually pretty good. So that's basically it for hard and soft natural wood as well as the engineered wood. Do you guys have any questions, either from yesterday or the short little remainder today?
Do you see moisture content playing a role in the natural woods?
Not so much.
No.
Not so much regarding as far as the tool or how it performs, or
Would you?
feeds and speeds.
Okay.
Yeah,
I
not
was
so
just
much.
gonna say, would you run it a little slower if it's got a lot of moisture in it, or?
I mean, if it's a little bit on the wet side, obviously I would say, yeah, you're probably gonna have to back off the feed rate a little bit.
Okay.
Because it's gonna be more moist, so more dense.
Yeah.
It's a good question. I actually I've never had anyone ask
Okay.
that. I've talked to customers for 20 years and I've never had anyone
Okay.
ask about the moisture content in the wood. Which
I
obviously
haven't
happens,
had
it absorbs
anybody
moisture.
ask me, but
Yeah.
I
I don't think it's going to affect much, but you would probably end up backing off on the feed rate just a little
Back
bit.
off just
I think
a
you would notice that it struggles a tiny bit, and it may even leave quite a bit of debris on the tool itself,
Mhm.
from just being sticky. in a
Yeah.
way.
Yeah, that's when I notice it, is like when you grab the chips and they want to stick.
They're
to
moist,
each other.
yeah.
Yeah.
Yeah. Then I would imagine you'll see it right away and probably hear it too, that it won't let you run as fast.
Yeah.
That, it'll struggle. So you
Okay.
probably would have to back up on the
Back
feed rate
down a little bit.
Yeah. Yeah. Yes.
I got a question real quick. Our high velocity,
Oh,
it's got that finish cutting edge and then the chip breaking edge on it.
yes.
I mean, compared to a standard chip breaker, chip loads are a little slower running, but we're gonna get that much of a nicer finish with that.
So the
high
reason,
velocity?
so the reason why we don't talk about that much, about that one that much, is because it is kind of a unique tool. It is, I'd say it is extremely difficult to use because it is a 4-flute cutter. So it is a 4-flute compression that's got 2 roughing flutes and 2 finishing flutes. If you calculate the feed rates, it'll put you like way over 2,000 inches a minute. It's extremely fast. So we haven't had too many people successfully using those tools because of how fast you have to feed them. So that's like the 60-600 series, if you guys want to take a look at that. It's on page 60. It is a great tool. Now, as you notice, there's only 2 part numbers in that series because over the last, I want to say maybe over the last 5 to 10 years, we've been shrinking that series down more and more and more.
Yeah.
And the reason why we don't talk about this one as much is because I have a feeling at some point Jennifer's going to take these out.
Okay.
It's going to become obsolete, and then we'll just continue making them as specials if someone wants it, because it is really that kind of an oddball where
Yeah.
we have maybe 5% of all of our customers using this tool. It does great. It is a rougher and finisher and a compression, but it's 4 flutes, so it is extremely. It's designed to
You gotta feed the hell out of it.
pause. Like
Yeah.
really,
Yeah.
it's really designed to run extremely fast. We have it. Like I said, there's only 2 part numbers left in that series. I think we used to have 12, and now every year we've been taking some out. And the only reason why we still have these 2 left is because when Jen does kind of like a sales report, if she sees that there's someone out there still buying this, and if they buy enough volume of it, then she'll continue to just keep it in the catalog just to eliminate making it as a special. Sometimes custom tools, I mean, it's not complicated, but it's just there's always a minimum quantity of 6 pieces on specials, and then
It's an extra step.
it's an extra step for them, and then sometimes they're just like, well, I don't want to go that route. I just want to be
Yeah,
able to buy
I
it.
just wanna
So
order it.
for us, if we have to keep a couple part numbers on the shelf and just, we'll probably run a batch of 50 pieces and it'll last us 2 years,
Yeah.
So,
Right. Okay.
test time, it's not really a test. It's just, what are the 2 different types of woods? So we have the natural and the engineered wood. And then what are the 2 different types of natural woods? So it'd be soft and hard. What are the 4 different types of engineered woods? We have particle board, MDF, plywood, and then obviously anything that's laminated, veneer, any of that. If you have a new CNC, so again, someone who's not very, maybe experienced in routing, so if it's a new CNC user using or cutting 3/4 inch melamine, so a laminated material, what tool would you usually recommend? So we kind of talked about, we would usually want to try to put them into that baseline compression, just the entry-level compression tool, which is the 60-100 MW series. So this just shows its diameter. And then if the customer is using a 1/2-inch diameter tool, what RPM would you recommend to start at? This one I usually disagree with, because it'll say 16,000 RPM, and that's great. So it's 16,000 RPM for a 1/2-inch tool. You're probably going to calculate a feed rate of about 700 to 800 inches a minute. So again, yes, that works, and it's great as long as you have big enough parts. If that same customer's got parts that are much smaller in size, then I would say probably 8 or 10,000 RPM, and then see what the feed rate comes out at that RPM. It just really depends. The other thing you can do is you can tell them, hey, instead of using a 1/2-inch diameter, not only we're going to run at slower RPM and slower feed rate to put you where you kind of need to be, but maybe we can go down to a smaller diameter, like a 3/8, which has a smaller chip load, which is going to result in a slower feed rate. You can always adjust a couple things. You can reduce the diameter, which is going to reduce your feed rate because the chip load is smaller. You can reduce the number of flutes, because less flutes would be less of a feed rate. And then obviously adjust the spindle speed accordingly to the size of the parts.
So if you're doing a small part, if you use a 1/4-inch bit, you basically go way less.
Yes, way less. Yep. And then we do have 1/4-inch, especially in the baseline compressions, for example. There is a 1/4-inch diameter compression still with a 7/8 cutting length, which is designed for your standard 3/4-inch bit material. And then that would definitely reduce your feed rate almost in half. I think the chip load on like a 1/2 inch is 21 to 23 thousandths. On a 1/4 inch, it's only 14 to 16 thousandths. So it's a huge difference. Yeah.
I use that a lot.
What's that?
I use that a lot.
Oh, okay, yeah.
Because my customer wants a lot of intricacies.
Yeah, if it's a lot of intricate cuts and stuff like that, yes. So lots of change of direction, very intricate cuts, small diameter, slow feed rate, slow RPM. If you can reduce the number of flutes, that's great too. So that's the other thing too in the baseline compression, the 6100 MW series, is that we also offer single flute compressions. They're pretty much like the only ones that are available with just a one flute compression. Now that one looks really odd. That's the one that we've had multiple people call in and say, hey, this tool is chipped, it can't chip. Because just the way it looks, if you have two flutes, it's more symmetrical and it just looks, looks more like a real tool, what a tool is supposed to look like. A single flute compression just looks extremely odd, which I don't even think we have one in here, but a single flute compression is just kind of an oddball.
You can still use a 1/4 bit to do a chamfer, radius, and all that.
Okay.
On the 1/4.
I see, yeah. Yeah, definitely. What is the default cutting direction? It's conventional for the most part. Again, when it comes to the direction of cuts, so climb cutting versus conventional cutting, the tool itself doesn't care. The tool doesn't care which direction you start going into, but it affects your finish. So if you do conventional and then you notice that you have a kind of a rough bad finish on the parts that you're keeping on the table, but you look at your scrap and you have good finish on a scrap, all you need to do is reverse the cutting method. So always look at the scrap, always, because that's the one thing that a lot of people overlook. It just falls to the ground. They, they throw it into a bucket or a garbage can. If your scrap has the finish you're chasing, all you need to do is reverse the cutting method, and then you'll get the good finish on the parts and then the bad finish on the scrap. There's some materials that are kind of more sensitive to conventional versus climb cutting. But majority of the time it would be a conventional cutting method. So if you guys don't have any more questions, we can go over the tooling blocks pretty quick.
I got a quick question.
Yes.
Sorry.
That's okay. No.
I got some customers that at some cabinet manufacturers that ask me about our crystal diamond coated compression tools.
So-
I know we have one in here, and it's a single flute, but we do have like the
PCD compression.
DFC compression.
Oh, okay. So the DFC compressions and the PCD compressions. Again, these are kind of things we don't talk about as much, but so the PCD compression, which is the 68100 series, on page 96, that is a tool for woodworking applications. So this is strictly for woodworking made out of PCD. It's only available as a single flute, so it doesn't come with 2 flutes or 3 flutes, just as a single flute, because it's very complicated since this is a PCD cutter, meaning it's not just a one-piece design made of one solid material, right? So you've got what's kind of unique on this one too. It's actually a high-speed steel body, so these are not even solid carbide body. This is a high-speed steel body. But you have, in order to achieve a compression geometry on something that is raised or tipped, meaning you have tiny little tips that are straight, in order to achieve a compression design, you have segments that are, so it's segmented, meaning you have tiny little pieces positioned in different spots to give you a compression design. So yes, we do offer one, PCD, which is basically the toughest thing on the planet, right? So this does have a pretty decent tool life. But there's a little bit of flex because of the high-speed steel body. Chip loads are very small on this, so you're gonna run it very slow. So for someone who's used to running compression tools, and they're definitely looking for a good production time, getting as many parts out of the machining process as possible, and used to running 600, 700, 800, 900 inches a minute with these, you're more at like 250, 300 inches a minute. It's pretty slow. So it's kind of a slow process. But then the other one you mentioned, the DFC coated compression. So DFC is actually, it's a carbide compression tool, but with a diamond film coating on it, which is the toughest coating you can put on a carbide tool prior before going into PCD tooling. That one is more for composites only. So that's more for like carbon fiber, fiberglass, Kevlar, stuff like that. It's the 66-800 series, I think.
Page 86.
Yeah.
Yep. So that one is on page 86. At the bottom of page 86. So you're going to see this is a multi-flute compression tool with the DFC coating. So 4 flutes or 6 flutes. The reason why we have more flutes is because you're dealing with composites. Usually with composites, you want more flute content. Very little chip clearance because you're creating dust. Carbon fiber, Kevlar, you don't get chips. It's just a pure dust, basically. So you're not worried about having enough chip clearance. This would pretty much 100% fail in a wood application because you just don't have enough chip clearance. You would get major burning issues, probably set things on fire just because it's got way too many flutes and not enough chip clearance for wood chips to actually be evacuated. So this is created for composites, that you pretty much just get dust when you're routing. But we do have it. Any other questions?
When cutting aluminum, should we just be looking straight away in the metalworking catalog?
Actually, no. So well, it depends. So if you're routing aluminum on a standard 3-axis, 5-axis CNC router, then actually the production cutting tools, and then we have all the aluminum router bits in here. The metalworking catalog is pretty much more specifically for milling, machining centers, 5-axis or 3-axis, closed doors, coolant spraying everywhere. Those are more like true end mills, where they have an extremely high helix angle, multi-flute, usually 2 flute, 3 flute, 4 flute, and so on, and more just for milling purposes. So all the aluminum routing tooling is going to be in the production cutting tools catalog.
Got it.
Okay. Okay, so hopefully everyone's in the same order, but if not, just search for the part number. So I'm going to kind of go over these pretty quickly. So the first one I have, actually you can look at both of them at the same time. So there's a 60-001 and a 60-037. These are basically roughing tools, but the difference between the two is that one's a low helix and one's a high helix. So we have, in our 60-000 series, we have 2 different offerings. We have high helix and a low helix. So the low helix is only about 10 degrees. The high helix, I think, is a 25 to 30 degree helix. They're identical as far as the geometry. It's a 3-flute rougher, specifically designed for roughing purposes. The high helix, we usually say, is more for people with high horsepower machines because it's got a higher twist, so it's going to want to remove the material much quicker. So you need a slightly more powerful machine. Usually, we would say anything that's maybe 5 to 7 horsepower and more. The low helix is useful for people that have lower horsepower machines, like 3 horsepower, something like that, 3 to 5. The high helix is definitely going to have a much faster chip removal, so it's a lot more aggressive, basically.
You find the high helix gives a better finish as well?
Sometimes a little bit, yeah. I mean, they're roughing tools, right? But yes. because of the higher shearing angle, the
Yeah.
higher helix, like we talked about the shearing angle.
Yeah.
So if you can come in and then shear the material you're kind of like slicing it away
Yeah,
versus
instead of peeling.
a straight
it,
flute or a low helix
Yeah.
just kind of hits harder, and then it can be a little bit more aggressive, than the finish. So yeah, these are the roughing tools. Next one, I have a 60-337 or 60-307. Again, these are going to be the chip breaker finishers, but one's so they're both 3 flute. Well, one's a 3 flute, one's a 2 flute. So the 60-307 is a 2 flute version. So it's got the horizontal notches on the tool, the chip breakers, and then the 60-337 is your 3 flute design. Identical pretty much, as far as the geometry, but 2 flutes versus 3 flutes. That's the only difference. These are the ones that you can use for softwood if you're having fuzzy finishes. You can use it in hardwood application. You can use it in plywood, any engineered wood. We have the upcuts, we have the downcuts, and then there is that compression tool as well that has the chip breakers. We talked about that. Okay. Next one I have is a part number 60-245. That one is the 3 flute finisher. So this is our 60-200 series cutter. This is the one that's specifically designed for final finishing purposes only. So it's typically used only as a secondary tool to take a little skin off the material and give you that ultra smooth finish. Equivalent to like roughly 120 grit sandpaper if you're sanding with an orbiter sander. Moving over to the right side. Yes.
How do those do like in a pocket? They leave a decent pour finish?
They do, yes. They have so not only it's a finisher, but it doesn't have a corner radius. So obviously you are gonna see some tool marks.
Yeah.
Because it's sharp on a corner. But these have a very low dish point angle because they're not designed to be plunged. They're not designed for, coming in and roughing. They're just finishing. So the dish angle is only 0 to 1 degree, so it's just a tiny bit of a clearance,
Yeah, it's a
so that
low
it's not rubbing on the bottom. But it provides a decent bottom finish, but obviously it doesn't have a corner radius.
Corner radius or a wiper.
So
Does a wiper even work in wood?
What's that?
Does a wiper work halfway? Well?
Wiper is more for plastic and aluminum.
Yeah.
We don't ever see any major effects in wood because it's just the way wood routes. There's not exactly.
Yeah, there's
it just
nothing
doesn't.
for it to work on.
Correct.
Okay.
So a wiper flat is very common in our plastic tooling and the aluminum tools, as well as the milling tools. On the milling tools, we always introduce.
Yeah, I had never seen one in
Yeah.
wood, so I didn't know if it's.
Yeah, it just it doesn't affect the finish. It
Yeah.
doesn't. You don't see any difference.
There's no point.
But so that's that finishing cutter. And then moving over to the right side, I have a part number 52-285. This is just that general purpose wood round. So 52-285, 2 flute upcut. The downcut version, again, like I mentioned, so if you happen to have a part number 52-285 and someone's looking for a downcut version of this, chances are it's going to be 57-285. 57 is downcuts, 52 is upcuts. We usually have a matching downcut to an upcut part. Next one I have, this is the one that's a little unique because, so I have a part number 57-279MD. The D stands for downcut, the M stands for marathon. So this is the marathon coated downcut spiral tool for doing like dados in abrasive composite wood, engineered wood. This is the matching downcut to the compression tools. So if someone's using compressions for all the through cuts, but then they want a downcut tool for doing some of the dados or channels or things like that, that's what this one is. And then because of the coating, it'll give you a much longer tool. This is what the marathon coating looks like in case you guys, want to see the difference. The one I have is very purple, but like I said again, it's normal to see slightly different hues. It may sometimes look a little bit more like, like this, or like this. This is actually the endurance, so not so much that one. But It's anywhere between purple, kind of a bronze, rusty looking color. Next one I have, we didn't talk about this one at all. I have a part number 52-280B. B stands for ball nose. So this is a tool with a rounded tip. So this is a ball nose cutter that's designed, it's a general purpose ball nose tool. You can use it in plastic, you can use it in wood, you can use it in aluminum. This is a tool that is designed for doing some sort of a 3D carving, shaping, anything like that. So typically what you do is, again, this is used more as a secondary tool for someone who's doing, let's say, kind of a complex curved shape. They would usually come in first with a square end mill or router bit and hog out majority of the material and leave a bunch of stairs everywhere. And then they come back with the ball nose tool and then they remove a little bit of the material and to get that kind of a curvy finish. So this is a general purpose ball nose. There's two different series. There's a 52-200B and then there's a 52-200BL. The L is an extended length. So the L is a longer version of the ball nose tool in case you have to get into some very deep pockets and do some carving or, like dishing inside a big pocket or something like that.
Marty,
Yeah.
could the 65-200 be used on wood as well?
You can. It's just quite a bit more expensive because it's more of a yes. So it's got polished flutes. It's like a superior ball nose tool because it was more designed specifically for medical purposes or medical customers that do a lot of machining in UHMW or like your knee replacements and things like that. So the reason why we have a 65-200 and the 65-300B series, which is on page 78, that is like an ultimate superior ball nose tool. It was more designed specifically for plastic, again, UHMW for medical purposes, because in the medical field, when they're machining parts, when it comes off the table, that is as good as it can get. They cannot do any post-polishing, they cannot do any buffing because it goes into your body. So they can't contaminate the material in any sort of way. But yeah, you can use it in plastic, you can use it in wood, you can use it in aluminum. It's just a lot more expensive because it's a very slow process to make those. We use a different grinding wheel to make those. So instead of a typical 600 grit diamond wheel, we use 1,000 grit and you flute it extremely slow to achieve that high polish finish. So it's kind of a slow process. So they work excellent, but they're just quite a bit more expensive. The next one I have, also we didn't talk about, it's a part number 56-285. This is a general purpose wood route, but in a straight flute design. So why do we have a straight flute? Every now and then, you may need to have someone use a straight flute cutter because of vacuum issues. So a straight flute cutter has a neutral cutting geometry, so it doesn't push or doesn't pull. An upcut will always have that slight tendency to kind of want to pull up and lift the parts. A downcut does the opposite, it pushes things down. So if you have someone who maybe is using a very thin sheet of wood, maybe 1/16 of an inch, maybe 100,000ths of an inch, and they're using an upcut spiral tool and they're having issues with the parts lifting off the table, before we go to a downcut, because again, downcuts, you're pushing and packing everything down into the cut. So downcuts are a little bit more challenging because you're recutting a lot of the chips, which again creates heat. So downcuts, yes, they give you a mechanical hold down because they push everything down, but you're recutting the chips, so there's going to be more heat. So again, before you go to a downcut, sometimes it may be beneficial to try a straight flute instead because it has a neutral cutting geometry. It doesn't push, doesn't pull. And it provides a decent finish, where they may be okay with the finish.
You remember that compression I was asking you about for 1/8" material? We wanted the L.
Yes.
We wound up using that 56-200.
Okay. It worked?
Yeah, I mean,
Yeah.
it was kind of weird. Their spindle was locked at 40,000 RPM.
Okay.
So,
Yeah.
we made the best of it.
Yeah.
But we
So
got the job done with this
that's
one.
that's a very good question. The reason why I was actually going to mention it, because, so again, the reason is we have a straight flute is because if you have very thin materials. So his customer wanted a compression tool because of how thin it was, and they wanted to achieve a good finish on top and bottom. The problem with a compression tool like this, and so imagine this compression is designed for a quarter-inch thick, let's say quarter-inch thick material, right? In order to make this work for an 1/8-inch thick material, this would have to be extremely short, and then you still need the overlap. You still need roughly minimum 60 thousandths of an overlap, but 90 is preferred. So if you have a 90 thousandths overlap between the upcut and downcut and the material is 1/8 inch, it leaves nothing for this, which would become extremely brittle, and it would pretty much just snap off or break off. So Lewis wanted a compression and see if we can make it with a short enough upcut length for an 1/8-inch thick material. We ran it by engineering, and unfortunately we said we can't do that. It's just going to make it so brittle and fragile that it's just going to chip off. So I'm glad that they ended up using the straight flute, which again is a neutral cutting geometry, so it doesn't push, doesn't pull, and it usually leaves a pretty good finish. So that's the 56-200 series. This one is a 56-285. And then if you guys want to move down to the lower tray, I think a lot of it is actually the same. So the first two I have on top, they're actually
Over there.
the ones we already talked about. They're
Sorry, thank you.
I don't even know this. Okay, I'll just leave it there for now. So the 60-307 or the 60-001 or the 60-307, we already talked about these. They're in the top tray, so I'm not sure what we have. But this is where we have the compression tools. So you can take a look at the 60-100 MW. That's the basic entry-level compression. I have a part number 60-123 MW, so that's a 3/8 two-flute compression. This one happens to be the mortise type. The mortise means it looks kind of like this. It's got the short upcut length and a much longer downcut. If you have someone who wants one compression tool, usually try to put them into the mortise type because it's more universal. They'll be able to do through cuts, no problem. They'll be able to do channels or dados, no problem, because of the short upcut length. So the mortise is definitely a lot more universal. So this is the MW series, so that's the baseline. Then the step up from that is the MC series, which is the marathon compression. So I have the 60-123 MC. Same style tool, but with the coating on it for better longevity. And then in here, you're also going to find the chip breaker compression, which is the 60-123C. C stands for chip breakers. Again, this one is, a mortise type, so it's got a short upcut, much longer downcut, two-flute compression, but it has the chip breakers. Excellent for plywood. Pretty much like the number one compression tool you can use for plywood purposes.
If they wanted the C coated.
Yeah, we can definitely coat it, yes.
But it's not a stock.
No, not a stock,
number
yes.
for it?
But we can do it with a coating. We've done those as special, yes.
Okay.
Again, we have a 57-279 MD. We already talked about that one. It's just a duplicate. There should be a 56-285. Again, that's a duplicate. We talked about that one. That's a straight wood route that has a neutral cutting geometry. The one that you guys do not have in your toolkit that I'm going to pass around is the brand new tool that replaced the Polaris. This is the endurance compression. I'm going to pass this one around so you guys can see what that looks like. Again, it's just a compression, but it's with a different coating. It's our own recipe, so it's a proprietary coating that we do here in-house. It's called Endurance.
Do you recommend having a coating for plastics for bits?
We do not. So it comes up all the time. So we have customers that call in and ask for like a normal old flute. They're cutting plastics and they're asking if we can coat it. We can, We don't recommend it because the reason is because on a tool for plastic cutting, you need that geometry to be as sharp as possible. So we sharpen the front of the tool to make it razor sharp. When you apply coating to the tool, you actually round off that cutting edge. You remove some of that sharpness away. And so the tool, they're looking for a tool that will possibly give them more tool life, but it's actually going to do the opposite. It's not going to cut as good. It's not going to give them as good of a finish because you're taking some of that sharpness away.
So basically, it's like putting a blanket on it.
Exactly. And then the reason why we don't typically put coatings on a tool for plastic is because plastic is not abrasive. So if it's a normal, standard, hard or soft plastic, it is not abrasive in any sort of way. It doesn't have any abrasiveness to it. If it's a composite plastic, something that has a glass content, meaning fiberglass, then that's a whole different ballgame. And then for that, we do have tooling that's specifically designed for like FRP stuff, fiber reinforced plastic. That'll be coated, but it's a completely different geometry.
So would that work for a bulletproof plexiglass? Because we do a few of those.
For plexiglass, we would still use an uncoated carbide tool, but a 2-flute, not a single flute, a 2-flute. For the bulletproof plexiglass,
Yeah.
52-600 series is what we typically use. So it's a low helix, old flute, double flute. That's the one that we typically use specifically for hard, rigid plastics, such as the bulletproof plexiglass.
Yeah, because we cut it on the saw, and right now they want more, detail.
Yeah. So 52-600 series is what I would try.
Which is the polishing tool?
The polishing tool is a 75-100 series. It's not in the catalog.
Okay.
But I can send you guys, if you want to give me like your email contact or something like that, I can send you guys a brochure that we have on the 75-100.
Okay.
What's nice about that brochure, it also has the actually recommended feeds and speeds because they're very, very specific. So it gives you the RPM, gives you the feed rate, gives you the how much to remove, and it gives you the cutting method. It actually is always plan cutting.
Okay.
So it's a 75-100 series. It's a diamond polishing tool. So it's a PCD polishing tool specifically designed for acrylic. It actually works very good in polycarbonate. It works very good in plexiglass. Because plexiglass and polycarbonate, you can't plain polish because it will turn black. It smokes and turns black.
Well, you can buff it to get it clean.
Correct. You can clean it up and stuff like that, but the beauty of the PCD tool is that it does polycarbonate, it'll do plexi, it'll do cast acrylic, extruded acrylic, and leave a perfectly see-through finish. It'll give you that optically clear finish.
Yeah.
It's a 75-100 series. I don't think I have plastic with you guys. Mike has plastic because it's coming up next. Well, first you guys are going to go to the routing lab, but then when you come back from the routing lab, Mike is going to talk to you guys about routing plastic, and I think we mentioned the 75-100 series. Yeah, of course. Yes. Yeah. I don't know why we don't put it in the catalog. It's we haven't had it in the catalog ever since it came out.
Probably because it's so finicky.
It is a finicky tool. It's also $2,000 a piece. It's extremely expensive. When we originally had them, we were not making them. We couldn't make them. It was someone else making the tools for us. We have then. So what happened is we I know a few times we decided not to put it in the catalog is because we had a hard time getting the tools. The company that we were getting the tools from, they had it, then they discontinued it, then they had it, then they discontinued it, and then they had a hard time making the diamond material, so then they completely killed the tool. They killed the line and they no longer offered it. Because when it originally started off, it wasn't a PCD, it was what's known as a MCD tool. MCD stands for monocrystalline diamond. So it was a crystal that is grown in a lab, kind of like, lab-grown diamond, like that. So it was a crystal that they grew in a lab, and then they had a hard time making it. And so they killed the line and discontinued the tool. So then they came out with a PCD version of it, polycrystalline diamond, which is an actual diamond that is kind of like brazed onto a solid carbide batting. And then, they come in little tiny wafer discs, and then you cut tips out of it. So we now use PCD. And then ever since it became PCD, we started making it here because we have capabilities to make PCD. But we don't roll diamonds. But yeah, I can definitely, if anyone wants that 100 series brochure, I can send it to you guys.
Is it just still that one pager?
It's just a one page.
Okay.
Yep. It's really simple. I think there's only
5 part
4 or 5 part numbers on it. There's a 1/4 inch, 3/8. Actually, no, there's a 1/4 inch, 5/16, and a 3/8. 3/8 is the largest diameter. I don't think we have a half. I could be wrong because it's not very popular. But I think we have a 1/4 inch, 5/16, and then there's 2 different 3/8 diameter tools in that series.
You're right, it stops at 3/8, but it's 3/16 quarter.
Oh, 3/16,
5/16,
5/16, and 3. Okay.
And 2
Yep.
3/8
Yep.
with 2 different lengths of
2 different
time.
lengths of cutting. Yeah. So that's the other thing too, is the longest cutting length that we can get on the polishing tools is 1 1/8, and that's on the 3/8 tool. So if you have anything that's thicker than 1 inch or thicker than 1 1/8, you're gonna have to get fancy. You're gonna have to, add a neck to the tool or have a custom tool made. We can't necessarily add an extra cutting length. That's the problem with PCD, is it is extremely brittle, and we're limited to how long of a cutting length we can make. Once it's too long, not only it's brittle, it warps. The tip itself, when we try to braze it, it'll warp, and then we can't keep it consistent. I've actually run that by engineering multiple times, because we've had people that wanted like 1.5 inches, and we said we can quote it with a no guarantee, and you're paying $2,500 a tool. It's extremely expensive, and not guaranteed that it's going to work because it may end up warping the tip itself. So, have you guys met Brendan? Brendan, I know he had an emergency yesterday, so he wasn't here. So Brendan is one of our engineers. So he works within our engineering department. Yeah.
Nice to meet you.
I'll introduce him pretty quick. So he does a lot of our 3D printing stuff too. He's involved in a lot of making the shop more efficient. So he designs and 3D prints. He's even brought in his own 3D printers into our shop. And then he does a lot of stuff for the shop, make fixtures, holders and all kinds of things to make it easy for the operators to have things to put into and stuff like that.
Mostly manufacturing control, process control, standardization, things like that.
Half the time when he tells me things, I'm just like clueless. I'm like, I don't even know. Like, it's extremely smart. We're smart guy. So
you guys should by hand.
I mean, you have how many printers at home?
I do not know.
Yeah. Yeah, he's shown me pictures of his garage. It's insane. So yeah, he does things outside and stuff. So, but yeah, you guys have any questions on it? If not, I think you guys are in the lab next, routing wood basically. So if you guys want to grab your safety glasses and your headset, then we can head out to the lab, and then I'm sure Gary does something as well. And then if you see me throughout the day, and if you guys, like I said, if you need anything emailed to you guys, just grab me and let me know. Perfect. Oh, you got, okay, cool. Yeah, remember, this is the one from our YouTube channel, I think, right? Yeah. Yeah, we have an actual presentation. I know you guys did all this. Yeah, James, that's good. Sure, so much, so good. Yeah. Yeah, perfect. Yeah. Awesome, yeah, you can share that with me, then I will share some of this people to myself. Awesome. So we've added, longer neck, but when you step it down, you end up seeing the line, and that's the problem with it too. So that, and then you're limited how long you can make it. So yeah, exactly.
Really? So then, can I just look at that? So I don't want to be involved.
No. Again, there we go. Are you gonna try and punch it up? Tomorrow. So you got tomorrow. And, yeah. I mean, that's why I was asking, are we talking about, so the first thing to do is go back, it turned out to be a little. Correct. Exactly. So, this is why I mentioned two different things, so that before potting it, we make it shorter, it's a lot. Yeah. We're making the cutting like longer, you can, well done. Exactly. Same thing with the overall length. Yep. The full 10%.
Yeah, we have routers, but
I don't, but I will, I'll send you. Is your cell phone?
He did say, he did say it was my fault.
Alright. I literally was gonna talk to you. Actually, right now, we're doing. We have events from these guys that.
Oh,
And so,
that's.
yeah, so the top, so White Oak. Now we're making these crazy looking. Yeah, they're super expensive.
Yeah.
Big size.
Yeah.
They break a lot. Never know what you're gonna get. This is their, basically like we had last night.
Yeah.
Just over there. Big circle. Super fast. That's 6 foot. Cuts that. Then we come
You're
back.
bringing the.
Yep, so that'll go up.
Yeah.
It'll spin super fast. Swing around on this machine.
But what I'm.
And then we have heads. I cut that. It's locked with the bears.
And how big is this?
Yep.
Oh, wow.
So they're tops are.
How big that like?
It's gonna be so
Yeah.
but.
You probably see where they go, man.
Yeah, so we've been testing, we've been doing that all week or 3 weeks ago. We're trying to figure out. Yeah, trying to figure out how fast. And they're yeah. I like that amount. Knocking around on the table, it's got to run. I think we saw somebody a couple times in a room, somebody's smashed it together,
Yeah.
then it goes on to the next, like, very, very fast.
Yeah, yeah, yeah.
I'll be honest, so they can't do it on the table, it just takes too long to put another piece down and clamp it. So it has to shoot into that same machine trap we're trying to design. It's all rubber bands and stuff, like, and then at the same time, we keep it faster.
It would make a difference.
Yeah, it'll be cheaper for them. It'll be less of a headache for us to make those saws.
Okay. It's
Okay.
gotta be 7 or 8
They're
years
called
old.
cartridges, that makes a difference.
Outlets, and I'm like,
We've got a lot
I
of,
can fix it all at once, full outlet.
if we can figure that out, that'll be.
And what is that?
A good way to do
That's just, the word they use for whiskey.
Well, you want to bring this to me?
Whiskey.
I don't know why we heard you.
Job title.
Rob does.
I mean, I drunk it. Yeah.
It's really cool.
That is pretty cool.
So much that goes into it. And
Yeah.
they char the barrels so the different ones.
Yeah, yeah.
All right. Good morning, everyone. Good night. This is the last time I'll be talking to you, so hope it's a good one. Wish everybody safe travels. Talking about machine plastics. What are plastics? Organic and synthetic components that can be formed or molded into solid objects. We use it all the time. It's inside of us. Major development started in the early 1900s. Plastics have that name because they can deform without breaking. They're used in every major industry. Large amounts of consumer products are possible due to the low cost and ease of manufacturing of plastics compared to when we were using metals and woods. Plastics can just do a lot more things. Plasticity is the general property of all materials to deform irreversibly, as opposed to elasticity, where it goes back, without breaking. But it's the class of multiple polymers that occurs to such a degree that that's why they got that name. Property is the key to making it useful. You can bend it and it stays there. It has plasticity. Great. So when we were talking about tools yesterday, we were talking about how the harder the material is, the harder you want your tool material to be. Plastic is pretty soft. Much softer than steel, much softer than carbide. You really don't use carbide tipped or PCD in plastic if you can avoid it, because they don't have enough break. So we don't have to worry about it being cut. What we need to worry about the most is having a sharp edge in plastic. Plastics need a much higher edge sharpness than other materials to cut, which is nice because if it required, a harder material required a much higher edge sharpness, the edges would break because the sharper you go, the weaker that edge is. So it's nice that it's soft. Soft and hard plastics, as I said yesterday, isn't really about how hard they are on the Bernal scale or anything like that. It's how they machine. So here are some examples of soft plastics: acrylic, high-density polyethylene, ultra-high molecular weight polyethylene, ABS, polystyrene, PETG, PET, polycarbonate, polypropylene, solid surface. Believe it or not, solid surface feels hard as heck. You got a lot of counters, but it machines soft. Under hard, we got acrylic, PVC, nylon, Delrin. I have seen soft nylons. Cast acrylic is hard, but extruded acrylic is soft. So we're never 100% sure, but in most cases, this is where it kind of goes. You can always tell by looking at the chips. The chips are big, curly, fluffy. That is a soft plastic. If the chips are sharp ice picks or grains, then it is a hard plastic. And use the appropriate tool for each one. Plastics, as opposed to woods, have a very narrow band of chip loads to get your great part finishes. You can see here along the bottom we have increasing feed rate, and along the side we have edge quality. I know yesterday I harped on always increase feed rate first. I still stand by that. It's better to go too fast in plastic because you won't get re-weld. You won't get breaking bits. You'll just start getting worse and worse finish because your bites are much bigger, so you'll start seeing it on your part more. You can always back off a little bit if you need to, but to find this part, which is where you want to be. But going too fast is always going to be better than going too slow because when you're down here, you get tool breakage. So feed rate up. The major tool geometries for plastic, O-flute. O-flute is the one you're going to want to use. Special cases and in hard plastics mostly, we got the V-flutes or Z-flutes, depending on how you want to look at it. I prefer saying V-flute because the OV is the shape of the flute, the empty space. On an O-flute, it's round like an O. On a V-flute, it's a V shape. Why are we all of a sudden taking the other flute into account too? I can have two O's next to each other. It doesn't make any sense. So I say V-flute because it doesn't look like a Z. It looks like a V when you look at the flute. Yeah, so mostly in plastics, you want the biggest flute that you can get. Single flute, very popular. Two flute, spiral up and down cut, 52-700. Every time, if you can feed fast enough. And then your straight O flutes. Here's how soft versus hard works. You get your curly, fluffy chip, And it's really nice when you have a round O flute to create that chip and try to help it to make the shape that it naturally wants to make. You're going to clear chips faster. Clearing chips faster takes heat away with those chips. Our tools last longer. We don't get re-weld. We get better part finishes. Everything's much more happy. Hard plastics chips into those flakes. Sometimes that's why a two flute V flute will be better, because it's just happier making those shards, just plowing into it, hitting it. It's going to break off a little bit, break off a little bit, and keep going. Standard tools, the tools that most people think of when they think of a tool that are two flute, three flute, four flute, have a web, the core. I think I used core last time we talked about this. The web or core of the tool is the center portion where the flute isn't. It's the area at the center that's a full cylinder that gives the tool its strength. When we send a chip into the flute by cutting through with the rake face and the clearance face on the outside, then that chip detaches and it goes into the flute. It goes until it hits the web, the part at the center, and I took the things away. I should not have done that. So if we have a shape like this, and this is the rake face and the edge, the rake face on the inside, when the chip detaches, it goes until it hits the center part, where it can no longer go anymore. So if you have a shallow flute there, it's going to curl a little bit faster. Can we kind of think about that? That makes a little bit more sense. So in order to get more fluffy round chips, we want that distance to be higher. We can use a bigger tool. That would do it, right? Because then we can go, there's more, the percentage of flute depth to core or web becomes bigger, so you just get more space in there. Or we can move to a smaller or a bigger flute shape by going down in the number of flutes. So that's why single flute tools are very popular when we're machining plastic, because it has all this space that it can go. The web, it basically just doesn't exist. There's nothing in the center there for it to hit, because we can go all the way below center. With a more standard tool, the web is much bigger and it has to curl faster and make it tighter. Not the end of the world. Some materials like that, smaller tools, but anything that you can do to increase that flute space when you're dealing with big fluffy chips is going to be a lot better, because then you can make it so that you don't have to force them into a shape they don't want to be in, and then they'll just clear naturally for you. I talked about a little about this yesterday with when I was talking about carbide tipped tools, anything with a straight geometry. The way to get rake is that we go behind center. So if this is the center line of the tool, we're back over here. That way when we rotate up to center, we have a rake angle, where with a round tool, we can just say that's the rake angle. But you can see more clearly the core here that we have. There is the core right there, anywhere between. That's a fully cylindrical spot. For plastic tools, we need more rake, so we move the flute farther back off of center line, so that when we rotate up, it has more rake. But that requires us to have a thinner flute as well, or a thinner web as well. So that it's a little bit smaller on this one than on this one. This would be for plastic. This would be for probably wood, something. Standard Z flutes, I mean, and you can make a V flute all the way to center and it just has zero rake. So if this was rotated, you'd have zero rake. And that is relatively common on wood tools. Usually it's a little bit farther back behind center, but it's not too bad. Any questions about that so far? I'm making this more complicated than it needs to be. Standard V flutes have low rake and a thicker web. Plastic ones have a higher rate and a thinner web. Higher rate means the sharper edges. V-flutes are preferred for hard plastics. Not going to be curling anything with the shape of that flute, that rake face. We're just going to be plowing in, shearing it off, and letting it do what it wants. But if we make that web smaller and we go farther back, it's sharper, and there's more space in there after it breaks off for it to break up even more and move out of the way of the cut. Because V-flutes are not helical, the chips aren't going anywhere. They're not moving up towards the shank or farther down. They're just going to fall where they fall. But it's still better to have a little more empty space in there where they can't clump up together and re-weld. In soft plastics, this is what I'm talking about when we get bad finish because of feeding faster. We just get knife marks where you see as it rotates around the tool, it's creating this little chip here. It creates a thing here as it's still advancing forward at the same time. And this part will be leaving a little bit where it's going from here and cutting to here again. It's just leaving a little bit of knife marks. You'll see that on the side of your part as a little bit of roughness or vertical lines, or if you're using a helical tool, there'll be angled lines. But you're not re-welding, and you're probably not breaking tools. So this is better. This is a good thing to see if you start off and you're seeing knife marks. Like, okay, I know that I'm not having any major problems. I can increase my RPM a little bit, because we never want to decrease feed rate first, right? To reduce this, to get better finish, when we're overfeeding, it means our chip load is too large. And another way to make our chip load smaller is to increase our RPM. So if I start at 10,000 RPM in this plastic, and I'm seeing some slight knife marks, I can go to 12,000 RPM and see if the knife marks go away without risking reheating that material up and getting a bunch of plastic re-adhered to the part or the tool or breaking the tool or doing weird stuff like that. Always feed first. Feeding too fast is usually not a problem. Yes?
In general, what's the least amount of RPM you can increase and see a difference? Is it about 2,000 or?
I mean,
generally,
yeah, about 2,000. I would do steps of about 2,000. But I'm also, if I'm sitting there, I'm gonna turn it up. And here I'm doing. It's usually a percentage.
Turn the dial.
So if you're at 20, if you program it 10,000 RPM and it lets you go 200% override, I'm going to go 10%. Does that sound okay?
Yeah.
And that's 1,000 RPM, so it's somewhere around. But yeah, 2,000 is where if I'm reprogramming, I'd be like, well, I'm going to go 2,000 RPM because there won't be an obvious difference.
Yeah, I have some. Well, let's increase it 200. It's like, why?
That's not a very.
That's not enough.
The thing is, it's not. I can't say in every situation would be wrong because there are harmonics at work too sometimes. So maybe you're at just a weird part of the power curve, or maybe there's like some sort of harmonic going on in the whole machine, and changing 200 RPMs might just make it go away completely, and now it's no longer vibrating. You can hear it. But yeah, if I'm reworking something, I probably go, okay, I'm running 10,000 RPM. It's a single flute tool. I'm doing 100 inches per minute. What is that chip load? Okay, it's a 10 thou chip load. If I go to a 12 thou chip load, are we now good? Or an 8 thou chip load, 8.3 chip load by going to 12,000. That seems like a reasonable amount to take off. Maybe I'd figure out how to make it an exactly 8 thou chip load. Really no wrong way to do it as long as we're following the basic procedure of feed faster. Oh, I got a little bit bad finish here. Let me decrease my chip load by doing something other than feeding slower. In hard plastics, we tend to not see those lines. We tend to see like a foggy edge or a fuzzy edge, that is the effect of cratering, where it just pressure is being exerted onto the part a little bit too much in that one area, and it doesn't like it, and it just kind of crumbles. We do use the 60-203 flute tool to finish slash finish cutout a skin or a tab cut. This is talking about finish allowance. So the diameter of the tool affects how much you want to leave as the extra. If you're using a very small diameter tool, you want to use a smaller amount of stock left on your part before you do the final cut. And a bigger tool, you can leave more material. With plastics, because of bounce back, you never want to leave less than 15 thou. So no matter what type of tool you're using, 15 thou is the minimum. And in plastics, more like, so it's, if you're used to machining, to milling metals or something, you might go a lot closer. You might be 7 thou or 5 thou from your finish, and you're going to come back and finish that. Plastics will have more thermal expansion and a more bounce back, so you want to leave enough that you can get a good cut every time where it fully engages and makes a good slice and not bouncing off. All right, let's talk about more specifics. Hard plastics. 56000P. There also is a 56000, I think, still in the catalog. So that is specifically different. Let's start bringing my glasses. Do this. Yeah, there's a 56000. We're not talking about that. We're talking about the 56000P, which is better for plastics. 56000 will also work on plastics, but it's just not as good. We don't recommend it. I don't know why it's still in the catalog. The 60-200, you can use it for machining hard plastics, not just for finishing. 62-700 is a single flute down cut for plastics. 63-500 is the acrylic tool, so good for both hard and soft acrylics. 63-700 is the upcut single flute hard plastic tool. The 64-000 is the down cut all arounder tool. So it can do plastics, hard and soft aluminums, even some wood stuff if you're doing trimming or things like that. The 64-000 is down cut jack of all trades tool. 65-000, exact same thing, but upcut. So default to the upcut whenever possible. Giving the tools helix makes the chips flow better, moves them away from the part. All of these tools should provide you a smooth finish in one pass. Using the 60-200 as a finishing tool might get you slightly better finish. Using the 75-100 PCD polishing tool should get you even better finish than that. Yeah, basically this is now talking about how deep can you cut with these tools. That's going to depend on the exact material. It's going to depend on your speeds and feeds. It's going to depend on a lot of things. So don't take this for gospel, but you can cut like 4 times D with 1/4 inch tools, and probably a little more than that with the over 1/4 inch tools. Anytime you're cutting with anything that's less than 3/16 or less, the flute space is small enough that it's harder to clear those chips and harder to move them a longer distances. So it is more difficult, but we can look at specific applications, and we do have a new series in here, I think, which is specifically for deep depths in plastic. One of the only new product development things that I was not involved in. So I can't remember the number. I think it's the 63-100 series. Yes, with super long lengths of cut for their diameters. And I'm going to say, again, I think I mentioned yesterday, when you're machining hard plastic, you can usually get away with using a soft plastic tool. It's not going to last as long, but you should be able to find a spot, feed and speed, where you get decent finish out of that tool. So in edge cases where there's a soft plastic tool that fits your needs and there's no hard plastic tool, you can kind of use that. Just expect slightly less tool life. Soft plastics, we got 11-00. That's a steel tool. Why would we recommend a high-speed steel tool? Because the edges of the high-speed steel are actually sharper than what you can get on solid carbide. The makeup of solid carbide, if you remember from yesterday, is like cement, it's particles. There's always some roundness to that edge. There has to be. That's just the way that the material is. With steel, you can have it come completely up sharp. Downside of that, you're going to wear it out really quick. Even though it's much harder than plastic, it's still going to wear out much more quickly. So in most situations, you're better with carbide. But in stuff like hot plastic, if it's coming out of a forming machine and you're like cutting tags off or something like that, steel can work. You can get steel to be longer because it's tougher, so you can oscillate, you can do other things. There are other solutions for hot materials, super soft plastics. 52700, best tool in the catalog. 52700 series is my favorite. Cuts so good, so fast, great finishes, pockets, everything. 56600, 61000P, there's a typo there, 62750, 63750, those are just the downcut and upcut soft plastic single flute. 64000 and 65000, same exact thing. You can use them on anything, jack of all trades tools. And the 60-200 series, in soft plastic, you would only want to use that as a finishing tool. You wouldn't want to use that as trying to cut the plastic out completely. But all these tools are going to have a little bit higher rate than the hard plastic tools, and they're going to be better in soft plastic, give you better finish, better tool life. If you tried to use a hard plastic tool in a soft plastic, you're going to run into real troubles. You're never going to find anything that works. Speed and feed is going to be really great to get you good finish, and your tool life is going to be very small as well. So you can kind of go from soft to hard, you can't really go from hard to soft. Free flow ship out and I do everything. Yeah, same things. High-speed steel for air routers, anything hand operation, high-speed steel, and also for warm condition parts. 4 times D, maybe 5 times. You have to find a special. And you almost always want to stop at 3 times D and do a second pass. Specialty tools for plastics. We have those edge rounding. It's like a thumbnail radius on the side of your part. At the same time that it cuts the part out. 66000 series, very good. There are single flute O shape. There are 2 flute V shape. They're available by the thickness of the material. So on that page, when we look at the 66000, on the right-hand side, you can see the plastic size. That's the thickness of the plastic that I'm talking about. So if you want to cut 8-inch thick plastic, you want to use maybe the 66082 or the 66085, depending on whether you want straight or spiral. And if you want to do 1/4 inch, you'd use the 66084 or the 66086. Not that hard to figure out, but something to point out. We can also make all these in specials. If you have a special size or you want a special radius or do anything like that. We do like flat and then chamfer both sides. We do all sorts of things like that. So this is something to keep in mind.
Millimeter too.
Millimeters, yeah, anything you want. Any sizes, any shapes, we do it all. Lead time on something like that would probably be like 7 working days. Specialty tools, route and chamfer. We also do the route and chamfer. It's at the front of the most. Better in hard plastics than in soft plastics, but we'll do a decent job with either. And the 66200 finishing tool. Talk about that. But yeah, the real reason you come to this seminar is so that we make you look at the catalog backwards and forwards a bunch of times because it doesn't really make a lot of sense. Next to the, I've been working here for years. 66200 is on page 80. Let me see that. Again, by material thickness. So if you want to route and then chamfer a 1/4 inch, use 66210. If you want to route and chamfer an 1/8 inch, use 66200. Because otherwise, you'd just be routing and not chamfering, or you'd be ruining your spoil part. 66300 series, bottom surfacing, works great in plastic, but they have radius corners. There's 2 of every size, one with a very small radius, as small as we can make it, and still get good finish, and one with a larger radius. The larger radius one is going to put a bigger radius in the corner of your part, but it's also going to make it a little bit easier to get feeds and speeds and everything on that. The bigger radius is a little gentler on the bottom of the part. So
you're looking at about a 1/2 inch, 3/4 radius?
More like 20 thou rather than, I'm sorry, 1/2 inch, 3/4 of the diameter?
Yeah.
Oh, 1/2 inch tool is usually what I would do. We do have a 3/4 inch. Yeah, it comes in like a 2 thou radius, and then on a 1/2 inch, it's a 30 thou radius, and on a 3/4, it's a 40 thou. So you can either do 2 thou on any size, or the larger radius is by size. Is there any other question about that? Pocketing or even just facing the top of your material. If you've got a small piece of material, the gauge length is too long, these are good tools to use to do that. I also always recommend the 52700. It does a really good job of this too. And you get sharper corners, but there's a chance. Teeny tiny chamfer instead of a teeny tiny radius. Plastic saw blades, something we haven't talked about at all, is saws. We don't really make a lot of saws, but we do make these for trimming. You could also use them for slotting. There's some other applications that you could do. The 70-100, 70-200, and the 70-300 series. The difference between the series I want to point out. The 70-100 series, you buy a blade, you buy an arbor, you mount the blade to the arbor and screw it in. You can replace that blade as you want. You can make it left or right hand by flipping the saw over. And you can use the same arbor for multiple different diameters. All of those are options, very nice. You cannot put the face of that tool onto your part. You have to cut from the side. With the 70-200 series, that is a flush mount. It's a flush trim bit. So you can go to the top and run across the top of that and cut things off the top or reduce the gauge height of that part. You can do sort of anything you want on there. The 70-200 uses solid carbide blades. So the arbor that is brazed to is steel and the blade itself is carbide. And the 70-300 uses the same blades as the 70-100 series. They're solid carbide tipped blades, but they are also, it is also a flush trim mount. So, variety of sizes, variety of numbers of teeth, fast feed, slow feed, everything's in the catalog. We can talk about it more if you need.
So how long is the lifespan on it? If you do a 48 by 96 sheet, 60 pieces, and using that actually decade.
In that particular case, I would not use that tool. I would use, in that particular case, a 90. 91-100 series tool. I would probably use the 91-114. And then I would replace the standard inserts with the radius inserts 91-127. So that's a 4-inch diameter tool with inserts that I can replace, and I'll be able to run it faster. Using this tool to deck something down is possible. You'd use it the same way as you would, but your heats and speeds would have to be dialed in. I've never done it, and I do not know how long the life of the tool will be. And in fact, we can never say what the life of a tool will be, ever. People call us up and ask, how long will this tool last? The only way to answer that question is, how many parts do you get with the tool when you run it? That's how many you should expect to get the next time. We can have some margin better. Because everybody's situation is different, everybody's application is different, everybody's materials come from a different supplier and all this stuff. So, and it's especially interesting when somebody calls up and said, well, how many parts will I get? I don't know what your parts are. Are you trimming the outside of a sheet and that's your part? Or are you making 10,000 little parts inside of a big sheet and those are your parts? It doesn't scale to us and we have no way of knowing. So we have our own internal testing that we'll run, and sometimes we'll do longevity testing, but our numbers wouldn't correlate to anybody else's numbers in the field. With that said, you could use this to do it, and I would expect you to get a dozen panels or something like that before you have to replace it. Probably not the most efficient use though, because like I said, the 91-100 series with the radius inserts, you can replace the inserts. You can go down to the flat and and it has other options that you can use with it. Like you can just use it to surface your spoil board. You can use the radius bits to also surface your spoil board. It's not a problem. They just work better than the square ones that comes together.
So what is the lifespan of resharpening? Is it kind of like one time and after that you go away?
We do not resharpen saw blades.
So if you take it to a tool and cut it out of these in here, resharpen it?
I don't know. I'm sorry, I just don't know.
Another thing to know too about these saws that my experience from the customer is the run out with the flush mount is going to be about 5 thou, where the arbor and the bolt on is going to be about 2 thou. So it's just a good fact to know if you have a tight tolerance slot, because there's only the width on these are minimum, in the catalog. So it's going to have a run out of 5. It's going to be 10 thou wider on the slot, just so you know. But it's a good thing to know when it gets to anything that's critical as far as the width of the slot.
So flat trimming parts, or removing excess material. This might be something you use instead of that 11-00 on a hot form part, depending on where the cuts are going to be made and how you have this. Obviously, if you're holding the tool like this and you have to cut something like this, that's great because it's cutting this way. If you have to cut something like this, now you have to hold the tool like this. So you need, a different part. You need to get a 90-degree, I don't know what they call it, armature, something like that. But yeah, you can put it in your spindle and it'll drive the 90-degree one, do something like that. But now you're looking at completely changing how you do that. And you can just change holding. Specialty tools for plastic, the 70-500 series plastic drill. I talked about this yesterday. It's a high-speed steel drill with special point. It eliminates all the wrapping. You don't get, when the wrapping happens with these big old plastic chips, I can pass these around, big old plastic chips, they tend to, more over here, they tend to wrap around the drill or get stuck in that flute, and then they touch the top of your plastic part, and now all of a sudden you can see a bunch of lines at the top of your hole on your plastic part, and that's not good. 70-500 series pretty much eliminates that. You can also use a little bit of soapy water, a little bit of oil or alcohol. That helps as well. It's always better belt and suspenders, these kind of things. No wrapping, no cleaning. Oh, and you don't have to pull it off with the end of the drill after every cycle. Got all the major sizes. Everything is good. All right, step-by-step recommendations. When someone calls you and asks you, hey, what should I use? This is kind of all that we went over yesterday with tool selection. What's the first thing that you ask? Hey, we got to figure out what tool you're cutting. I need to know what material you're cutting. What tool you want to use to cut, I need to know what material you're cutting. Are you using a CNC machine or are you doing a hand routing this? For new CNC users, which is a lot of people, start at the baseline single flute, O flute, 65-000 probably. Or if they know what plastic they're running, and you know that it's a soft plastic, 63-750 because that's specifically for soft plastic. But you want to default to the single flute because it's going to have the lowest feed rates. And you're like, wait, I want them to have high productivity. Yes, but if you give them something that has to run too fast and their parts are too small or their machine isn't capable, they're never going to be able to actually hit the feed rates that they're programming, and they're going to get upset with the tool. And they're going to be like, your tools are bad. It's not the tool are bad, it's that we can't feed the appropriate chip load. Use upcut for slots, and where top to edge finish is not critical. You'll never hear anybody say that anything is not critical, so I don't know when we can put that. Down cuts where the top edge finish is the key, but remember that if you're going to do that, you need to not be slotting, or you need to have really, really thin material, because otherwise you're shoving hot chips back into your cut, and you're going to have rewelding problems. Down cuts can also help holding parts onto the table. Again, better not be slotting, or better be a really, really thin material. If the tool that they want to use is above 3/8 of an inch, you probably, now is the time to go to a 2-flute. Depending on certain factors, that might be a 1/4 inch. 1/4 inch should be your default for everything, basically. Unless the customer requires a smaller bit, just stay at 1/4. And unless they're like, we really need to increase production, stay at 1/4. Because going up to 1/2 inch in a single flute is unbalanced. It's not as good. You can do it, we make them, but we generally don't need that much flute space. And going to a 2-flute tool on a 1/2 inch means you're going to have to feed a lot faster, because now you're doubling whatever feed rate you were talking about before. And if your customer isn't sure that they can make that 400 inches per minute on their, 8-inch part, which is the answer is they can't, then they're not going to be able to actually hit that. They're going to need to run their RPM really slow. Maybe they're out of the power curve on their machine, or if you run into more issues. So single flute upcut is the default. So in this case, we're assuming a soft plastic, let's say UHMW. We've recommended, we know it's a soft plastic. Okay, single flute upcut, that's the 63-750 series. We go to the back of our catalog. We find the soft plastic cutting data, and we go down and we find 63-750 series. Assuming we're cutting 1/4-inch thick plastic, we're fully slotting it. We go, okay, well, that's 1 times D. We're good there. Go across the 1/4-inch. It says 8 to 12 thou. We're probably going to use 12 thou because we know it's plastic and we don't want to be on the low side. So these are completely wrong. They're just wrong. That's crazy. Nobody's actually going to hit their speeds they're looking for. You can use faster for smaller diameters. It's a surface footage thing. We don't really talk about it here in this seminar, but theoretically going faster RPM for a smaller diameter tool will get you good results. I almost always start at 10,000 RPM, regardless of diameter. It's a great place to start when you're routing plastics, until you know something about, is it really big or is it really small? Yes.
10,000?
10,000. 10,000 is where I personally always start in plastics. Other people will be 12. Some people will be like, well, yeah, I know 8 when it's an 1/8 inch and 14 when it's a 1/2 inch, or have other things. I personally, 10,000, it makes the math easier, so that's nice. It also makes like programming easier. If you're like, you know what, I want to double, I'm not sure, I think I'll be able to run a lot faster. You can double everything, and then everything goes in 10% increments. It just makes it nicer on the machine. So ignore these, make a note in your notebook. These are wrong. Then we calculate what it is. Ship load for the 63. Oh, this is a different tool all of a sudden, because this is a hard plastic tool. So, that's a mistake. We should mark that. They want us to use 18,000 RPM. Okay, let's assume we're doing very long lengths of cut. We're actually going to hit our feed rate when we do this. We use 18,000. We multiply it by the 12,000 we got from our last one. And it's a single flute tool because we know it's a single flute upcut. 216 inches per minute. 216 inches per minute is very doable by most machines, regular machines that we're going to use, as long as we're not doing super, super tiny stuff with lots of detail. We're going to hit 216 pretty regularly, pretty reliably. Not in the first 2 inches of each cut, like any corner, we're not going to hit that. But overall, throughout the part, we'll hit close to 216, and we're going to be successfully clearing hot chips, and everything's going to be nice and cool, and we're going to be good. What happens if we go to the 52700 1/4-inch tool? Let's look it up. 52700 is a 2-flute tool. We're going to go to soft plastic. We're going to find 52700. We're going to go across. There's nothing under 1/4-inch, so we keep going to the right, and we find that it says 12 to 14 thou ship load. Yeah, if there's nothing there, just keep going to the right until you actually hit a value. Some people get caught up by that. So we'll just stick with 12 thou ship load. 12 to 14, it's probably more. I can probably run it at 18 or a 20 because 52700 is a very good tool. So I could probably make this 20, but let's just stick with the low end and go, okay, 12 thou. But now we have 2 here.
Yep.
So this becomes 432. A lot of places, there's a lot of parts, you're not going to actually hit 432. So now we're going to not be able to, now we're going to be underfeeding. Our actual ship load will be lower than what we actually tried to tell the machine to do. So that's why we stick with the that's why we stick with the one flute tool instead of going straight to a two flute tool. If we know that, hey, it's a really big part and we can go definitely faster than this, then I might do the 52/700 quarter inch, but I might assume, and maybe I even start at a 12 thou, but probably not. I'd probably go to the high end or even higher. And I'd start my RPM at 10,000, and now 10,000 times 12 times 2 is, what is that? 6 thou chip load? Yeah. Let's see, 0.012 times 2 times 10,000, 240 inches a minute. Again, we are achievable. 240 in the same part, it's achievable by simply moving our RPM down to 10,000.
And if you are doing 3/4 to the cup.
If I was doing a 3/4 depth,
Yeah.
half of that.
Yeah.
Yes, exactly. So we would be at 240, we'd be at 120.
120.
We could do 3/4 of an inch deep at 120 with the 52/700, and we'd be perfectly fine with that. Yeah. And then in that case, maybe, well, 120, we're definitely hitting it the entire way. Now I can put my RPMs up more and feed faster. I can say, okay, well, no, I know I can hit 240, so I can go at 20,000 RPM. As long as I'm hitting 240, it should run perfect because my chip load is the same. Should be good. Does that make sense? All right. Any questions?
If we are doing really small pieces with plastic, I used to leave tabs.
Leave tabs, yeah.
Yeah, but how to avoid that? The tool.
How to do it with the tool? I mean, that's a programming thing. Leaving tabs is a programming issue. You just move up 30 thou and tell it to move up 30 thou and move over a quarter inch and go back down 30 thou. You have to, a lot of programs will do that automatically. You say leave tabs,
Yeah.
and it'll do it. It won't affect your feeds and speeds at all. Should be the same. It will technically be traveling more because it's going up and down, and your Z travel might be slightly different, but you program it the same way. It's such a small difference, you just program it the same way. Yes, sir.
The plastic drills,
Plastic drills.
no pecking, right?
No
Just
pecking.
Send them home.
Just send them all away.
Okay.
You want to go high feed rate.
Oh, yeah,
Yeah.
absolutely.
High feed rate on the plastic drill, same as all other plastics, err on the side of more feed. I will note, good, thanks for reminding me, for all drills in the back, so we've done calculations based on inches per minute. When we do all of our calculations so far, when you do drills, you do inches per revolution. Drills you treat as if they're one flute all the time, just inches per spin. So the numbers in here, you don't have to multiply by, it's a two flute tool, you don't multiply it by that, you just go straight to RPM times your inches per rev, which is in here. That makes sense? All right, I saw there was
Better to size up and use different size diameter drills versus what I find myself on the production side, if I'm doing something, let's say I'm cutting some like AR2 polycarbonate and or maybe like a hospital or a behavioral health where they need something that's hard, you step up to hard since it's coded for that. But maybe we're perforating, right? So maybe doing on 3/8 bullets, I'm cutting the whole thing. That I'm just utilizing like a helical entry and route that something, or I might just peck through it and then run at my final down. Or is it better for me to just to spend the money on the drill bits and use that process?
My answer to that is going to be drill is the best thing to do. Make a hole. A drill is always the best thing to use. Where the rubber meets the road on this one is, does it make sense for your tool change to do, like, you have to actually look at the whole process. How many different size drills will you need? Do you have tool changes? How much will that tool change affect your final runtime, your productivity? Using a router bit to circular interpolate a an exact size hole, drill the hole is very common. People do it all the time, especially when it's big, right? So if you're doing a 4-inch hole, I'm never going to tell you to use a drill for that. You could use a drill for it. It would be better, go faster, and last longer.
One set.
But it really probably
We don't
doesn't
have
make
as
sense
many
to
of
buy
them.
4-inch diameter drills. If you're making a 3/8 inch hole, you're making 53/8 inch holes on your part, rather than circular interpolating them or packing them with a router bit, using a drill is the correct answer. Because you're gonna drill a lot faster in that plastic with a drill than circular interpolating or packing or doing something, and anything else. If you're making 2 holes in that same part, now you're like, well, it's probably not worth having the drill come out, drilling 2 holes, then tool changing. It's kind of, you'd have to actually do the math. So it depends. Did I answer the question?
No, yeah, absolutely.
Okay, yeah. Any other questions? Yes, sir.
So for the drill cutting data recommendation, you said that this is the IPR you should look to.
Correct. For
So
drills,
you
it's
don't have to multiply by
IPR.
2.
Don't multiply by anything. It's just that number times the RPM that you're doing. Also for drilling, you generally want to use lower RPM than you use for routing. Routing, when I'm saying 10,000 RPM for routing plastic, when I'm drilling plastic, 4,000 RPM, real low. You don't need that much horsepower, so you're generally not worried about being in the low part of your torque curve on your machine, if that's something you're concerned with. It will work at higher RPMs, and you'll be able to go really fast. Most machines can't Z feed that fast, so you gotta use your lower RPMs. But hey, like all of this stuff, this is where you start. Try out something different. You're not going to break the machine. Well, assuming nothing crazy, you don't do anything absolutely crazy. But yeah, if you wanted to try, my IPM on this is 10 thou, and I want to go at 20,000 RPM and just try and feed that fast Z, give it a shot. The worst that can happen is that you just get a bad hole. More questions? Countersinking. Depending on how much countersinking you're doing, you can approach it in different ways. If you're doing a lot of hole with a countersink, we make drill countersinks as specials. So we could make you one specifically for that application. That will be your best solution. If you want to just have something that can have one tool that can do a multiple sizes, and it doesn't, you're going to be putting a screw or something in there, it's going to be hiding it, it doesn't matter. Use one of the carbide tipped angle bits. So either the 37-80 or like the lettering bits or the 37-50 or 60 series work really well. That's a solid carbide or a carbide tip depending on size. And then you just go to the same spot where you already have a hole that you've done some other way and just go as deep as you want to make the countersink that you want and get the angle that you want. You can do all of that stuff really easy there. The finish is going to be fine, okay, not great. You could also do more interesting stuff like using the engraving bits that we have in here.
I was trying to get the 50 on it, but wasn't sure if how much of a finish will not finish.
Yes. The finish. So when I say don't use solid carbide tools for plastic, it's not like it's the end of the world. You can find something that will be an acceptable thing, especially if it's not in a place where people are looking. You don't want to cut your parts out with them because it's not really efficient, but a little pop on putting a countersink in, and then you can use one, you can get one big 90-degree one and use it for everything, if that's fine, or you can get an 80-degree one and use it on, and just how deep can you go, depends on you do the calculation, depends on the thickness, depends on how deep you want it. Anything else?
The frosted edge that you see sometimes on cast acrylic on the same cut, we talked about feeding too fast and breakout that can come from that. Is that frosted edge on cast and acrylic considered a defect?
Yes, that would be usually from cratering. That's the cratering effect when you see that frosted edge. It would be really cool if I could tell you exactly how to make that happen every time, because sometimes it looks nice, but I can't. There's no, if you find a specific tool that makes that happen at specific speeds and feeds, it's a happy accident, and then you gotta go ahead and do it. But usually it's inconsistent, right? So it'll happen for an inch and then stop, and then happen for an inch and then stop, and won't really keep it. It generally happens from overfeeding in hard plastics like cast acrylics, or sometimes it can happen from using soft plastic tools in hard plastics. And because it's sharp enough that it's actually pulling a little bit of it out each time it's cutting, but the tool is going to wear pretty quick and might not do it. So we have actually looked at that before in like happy accidents have happened, or we made a tool, send it out for testing, and the guy's like, oh yeah, it makes this really great frosted edge. I want to use it on everything. Can you make me that tool again? No, we can't. Anything else?
Totally unrelated, but when cutting fiberglass, you don't need to worry about the chip clearance because the chips itself are dust. Okay.
The chips are dust, yes, but they are hot. When you're cutting fiberglass or any composite thing, they tend to be hard resins, hard plastics, so they will create really, really small, sharp chips like hard plastic. They are hot, they will re-weld. If you do not get it out of the cut, it will stay there, clump together, smolder, turn on fire. You'll see, I've had flames come in the lab. Yeah. Mostly it'll just re-adhere to the side of your part, and you'll have like dust and then like a big clump of dust and then dust and a big clump of dust. It'll re-adhere to your tool, it can cause breakage, it can cause fires. So it's hard to control. We use a lot of burrs for fiberglass and roughing tools and stuff with roughers on it or chip breakers to try and control that, to break them up further so that they'll scatter more, basically. Because if you can pull it away with your vacuum, with the dust collection, that's great before it can like clump together and be like, if it's a little particle by itself, it loses its heat very quickly to the atmosphere. It's when they're close together and they can keep that heat that they clump together and then becomes a fire hazard that you don't want to deal with. But yeah, I don't want to give the impression that they are chips. It is dust, but they are chips and they are hot. So you do have to be worried about what's going on with them. So always better if you're cutting fiberglass or composite to be up on pods or something where the dust can fall and has time to lose its heat before it is all in the same place. If you're doing a small part or something where if you're on the table and you're creating all that stuff, it's getting really hot and then just sitting there with a bunch of other stuff that's really hot can cause a problem.
Okay.
There was another one. Adrian? No? Anybody else? Okay, one more.
On the cutting tools, let's say it's showing a quarter-inch diameter tools cut one diameter in half, right? So on a 3/8, you're saying that I can cut a 3/4-inch piece of material in a single pass.
One and an 1/8 inch. Single pass. Right, a 9/8 down.
Okay, so I'm looking at this as under quarter of 3/8 diameter, two diameter times that.
So I think this is a little bit of a weird typo in there, but.
Yeah, okay, it is weird.
46, so.
49. That's not exactly fishing material, yada, yada, yada. The standard disclaimer, but yeah, in general, 3 times these with a helical upcut tool, very doable. And it's just 3 times the diameter of the tool. So if you have a 1/2-inch tool, 1.5 inches thick, you should be able to do that.
For some reason.
Maybe it's hard plastic and your black isn't good, or your hold down isn't good, you might lose your part. like your pressure is getting higher too, so, you know, there's things to do about that, but then you can just do 2 passes instead of do 2 3/4 passes. That'll be lots of pressure.
Is there a best practice, and maybe this errs on the programming side, but it's pretty full path. So if I'm cutting, let's say some HDP, I'm using 60 from the 776. It's a typical tool that I'm utilizing for that. I'm gonna ramp into it, but then typically I'm gonna do a depth into that. Okay, it's just I'm getting an easy finish from off on a ton of material. Is that just for school life, or am I wasting time in the production?
Assume you're not moving your part, everything, like, a program that works and does the job is the right way to do it. To iterate on that, to try and improve it, you need to do a little bit of experimentation. So if you're doing, it was a 1/4 inch, 3/8 inch, so it's 675?
That 1/4 inch.
1/4 inch tool, 63,775, you're doing it 1/4 inch at a time?
I'm typically doing a depth ramp, so I'm just running it all the way down until it makes it to that 3/4 and then doing a final pass at depth.
That is exactly what I would do. That is the most efficient way to do it. Like just going all full depth of however deep you're going to cut on your part in a ramp. Right?
I ramp the whole path, the entire outside.
Oh,
I'm ramping the whole thing down. So I'm starting at 1/4 inch.
no, I wouldn't ramp for more than, I mean, how thick is your material?
3/4.
3/4, I wouldn't ramp for more than 10 inches. That you probably feel it, but just probably 5. Yeah, just ramp to final and then come and go to the point where you ended your ramp. That should be perfectly good. The only reason that it wouldn't be is if your hold down wasn't sufficient to keep your part. Right? Because when you get to, if you're ramping around the whole thing and then going around again, you will have much less pressure sideways as you're doing it again. Because you have all the vacuum still and you're not making part of it. That's the only thing I have to worry about. But yeah, you shouldn't be able to just take whatever the total length of your part out, take everything 5 inches out of that and save yourself all that time. Yeah, I'm pretty confident in that one, in that particular application. I'm pretty confident that will work. But yeah, you know, it depends. Yeah. All right, I think we're done. Thank you, everybody, for your attention. Yeah, you can look through the boxes if you want, look at all the tools. I described them. The catalog is there. I hope everybody has a great trip, and I hope you had a great time here.
Thanks, Mike.
Yeah. In 2020, when I decided that machine doesn't have fiber time, every single time,
Look at that. Yeah.
Every time we lost it. I thought that was
What tool are you using?
That's what I'm gonna find out. I have a bunch of notes around school. I was using a 422.
Oh,
and I was crawling.
You're the opposite. You were consistently getting the opposite. This is Rewell. You're experiencing Rewell. So you're making such tiny chips that the chips themselves are adhering to the size of the part. But they're super fine, and they just it's plastic. You melt it and stick it together. It stays together. That's exactly that has to be that.
Yeah, I had no idea what was here. I
mean, it looks nice. It looks really nice. It looks really good. Yeah, and you can do it with like special post-processing things, like but yeah, you need all this stuff special. But if you can get it, great.
And then when I get jumped out of that,
Thank you. Well, it's not that then. That's not actually a burn. It's got a small cutting edges and all. Yeah, that comes to a straight point.
So it's not a bit of variation, so on the back.
Yeah, this, the multi-flute composite router. Yeah, multi-flute composite router, there's bigger chips on there, faster feed rate, and lower RPM. Probably running is RPM, well, it might go a little higher in composite. Carbon fiber, you know, I've had carbon fibers that I've cut at 6,000, and I've had carbon fibers that I've cut at 14,000. It depends on how much. If he has what the percentage of resin. He probably knows. He's never cut it.
You can't get, I was just cutting the corners with four minutes. So it is like, put us up, but also give it a I'm sorry.
Lower RPM, I think.
Yeah.
But you start at 6%.
What is it about the
Feedback that lot. Treat this as a one food. Don't, there's gonna be a lot of foods, anything that has multiple materials, kind of all the same. I think it's actually say how many things there are in this. Don't follow that. Don't follow that, treat it as one, whatever's in the back.
Hey, I actually want to say this to everybody. He just pointed something out. In the back of our catalog, for anything that looks like a burr, it sometimes says how many flutes are in it. Ignore that. Anything that's a burr, treat it as a one flute tool. So our multi-flute composite router, our high performance composite router, all of our burrs, don't try and count how many flutes or look at just the number in the back of the catalog times your RPM, that's it. Treat it as one flute.